Hello, good morning. This is Pedro.
Yeah, good morning, Professor Pedro. Can you hear me?
Yes, I can listen now. It's
Yeah, welcome for joining. We will be starting soon.
I think everything is ready from my side, so good luck for you.
Ajay, am I audible?
Yes. Yes,
Okay, good.
So, good morning and good afternoon to everyone. Distinguished delegates, participants, and my dear colleagues. This is Dr. Ajay Kumar, Assistant Professor, Department of Mechanical Engineering, IIT Guwahati. It is a glorious moment to extend my warm wishes on behalf of the organizing committee for today's international webinar on advances in materials processing and mechanical testing. I want to convey my heartfelt gratitude to all the distinguished experts from USA, UK, and Finland for accepting the invitation and presiding over this webinar on advances in materials processing and mechanical testing. It is an opportune moment to refurbish and discuss upon the recent development in the advanced materials processing and mechanical testing and its future opportunities. The webinar on advances in materials processing and mechanical testing aims to bring together international leading academicians to share their experience and research findings in all aspects of advances in materials processing and mechanical testing. It also provides a premier interdisciplinary platform for researchers, academicians, and industry colleagues to discuss the most recent innovations, trends, and challenges encountered and the solution adopted in the field of materials processing and testing. So the webinar will focus mainly on advanced materials and processing, artificial intelligence, and big data in manufacturing. So I would like all of you to welcome or joining this webinar. Now I request Dr. Madan Mohan for opening remarks. Dr. Madan Mohan.
So thank you, Dr. Rajay. So, coming in, director, distinguished speakers, colleagues, and students, and participants of this conference. Once again, I welcome you for the student webinar on advances in materials processing and material testing. So, first I would like to congratulate Ajay and the manufacturing team for calling us distinguished speakers across the timelines and bringing them together and organizing the students webinar. So as Dr. Ajay mentioned, so this is this area of materials processing, invention of the new materials, to use them, this materials processing and testing is one of the much needed area of present time. So this is a very, I'm sure that you are going to benefit from this such a distinguished speakers in these 2 days. So I just would like to introduce, give a brief introduction about the Department of Mechanical Engineering. As of now, we have Department of Mechanical Engineering has started along with Institute in 2015. We started offering Bachelor BTech in Mechanical Engineering. In 2017, we started, in August, we started MS program in Mechanical Engineering. And 2017 December, we started PhD programs in Mechanical Engineering. So in 2018, we started MTech program also in design and manufacturing area. as in January 2021. So we have about 150 undergraduate students, 20 MTech students, and so we have about 45 masters and MS and PhD students. Along with we have 13 faculty who are very active, regular faculty who are actively involved in research. So we take like a manufacturing group, we have 4 faculty. So design group, we have 5 faculty, and we have 4 faculty. So and we do work on interdisciplinary areas spanning this across these disciplines. So we, as I said, the faculty are actively engaged in research and consultancy. So at present, we have about 25 sponsored research projects, which is amounting to about 100 million materials. So this is about the department that we do the faculty mechanical design. We have energy works in the area of composite materials, sort of guiding us in establishing the department. And then we have Dr. Sriram Sundar, who works in the area of noise, vibrations, and acoustics. And we have Dr. Venkatraman Pandrangan, who works in the area of again fracture mechanics. And then we have Dr. Anup Basak, who works in the area of computational mechanics. So that's about a design group. And then when it comes to manufacturing group, so we have very active research faculty doing active research. So we have Dr. Venkaya, who works in the area of metrology, and then Dr. Ravi Shankar, who works in the area of abrasive or finishing process and machining processes, and then Dr. Kiran works in welding area, and then so Dr. Ajay, who is the main the person behind this workshop, he works in the area of advanced materials and processing. So when it comes to thermal group, we have Dr. Anil, who is our Dean of Sponsored Research. He works in the area of energy storage and hydrogen storage. And myself, Dr. Madan, who works in the area of combustion and sprays. And then we have Dr. Balaji, works in the area of wind energy. And Dr. Girish works in the area, Girish Kumar Rajan, he works in the area of analytical and theoretical fluid mechanics. So this is about the department in a nutshell. So with this introduction about the department, and we are also, as I said, we are also looking for active collaboration in emerging research areas across the world. So yeah, this is, I hope, with such an eminent speaker, distinguished speakers, I'm sure that all who are attending the conference will benefit, will gain ample knowledge. So with these words, I thank you everyone. I wish all the best for this webinar. And I request our director, Professor K. Satyanarayana, to give his inaugural address. Thank you, sir.
Okay. So thank you, Madan, and thank you, Ajay. Welcome to everyone to this international webinar on advances in materials processing and mechanical testing, being hosted by the Mechanical Engineering Department of our institute. And since we have a lot of participants, not only from our institute, but from other places, I thought I'll use the opportunity to inform people about IIT Tirupati, where we stand, and why we're doing this workshop, this webinar. IIT Tirupati, as briefly mentioned earlier by my colleagues, started functioning in 2015. So we are third, as we call ourselves, a third generation IIT. The IIT system started in the 1950s. We had the first generation IITs, 7 of them, we consider them the first generation IITs, the first 5 at Delhi, at Kharagpur, Bombay, Madras, Delhi, and Kanpur, and then subsequently at Guwahati and Roorkee. These 7 we consider them the first generation IITs. In 2008, 8 more IITs were started, which we consider the second generation IITs, the ones in Hyderabad and Jodhpur and Mandi and so on. And in 2015-16, 6 more IITs were started. Now these IITs were started in Tirupati and Palakkad. These 2 started in 2015, and both of these have been mentored by IIT Madras, from where I come. And the other IITs that started in 2016 includes the ones in Dharwad, in Bhilai, in Jammu, and in Goa. As any new institution, we have it takes time to get ourselves established, but we at IIT Tirupati are growing quite fast. We started operating from a temporary campus, which we hired some buildings to get started off in 2015. And we started with our undergraduate programs in 2015 in 4 branches, in civil engineering, mechanical engineering, electrical engineering, and then in computer science and engineering. And subsequently in 2017, we started our PhD programs. And our master's, MS, Master of Science by Research, both these programs started in 2017. So early on, we started our PhD programs. And in 2018, we started our MTech programs. For example, in mechanical engineering, as was pointed out by Madan, we started the MTech program, Master of Technology program in design and manufacturing. And similarly, we started master's programs in other departments, including electrical and computer science. And last year, in 2019, we started the MTech programs in civil engineering, and this and also the MSc program in mathematics. And in 2020, we also started MSc programs in physics and chemistry. So we are expanding our programs, and we also started our chemical engineering bachelor's program starting from 2000, the batch that joined in 2018. So as we grow, today we have about 1,050 students on campus, of which more than 150 students are PhD students. So our PhD program is getting very well established, and also our faculty members, though most of them, though we started in 2015, most of our regular faculty members, full-time faculty members, started joining here in 2017. Before that, we had faculty members coming from IIT Madras and other institutions to teach the students. So essentially, we have had faculty members here, on a full-time basis for a little over 3 years. Today we have about 92 faculty members, full-time faculty members on campus. And they have been very active in research, with over more than 60, nearly 70 sponsored research projects that the faculty have brought in this very short time. So that's been another achievement in terms of giving a lot of impetus to research from early on. And when we started IIT Tirupati, for those of you who are from not from India but from outside the country, so Tirupati is one of the most famous pilgrimage towns in the country. The temple here is visited by at least 50,000 people a day, if not on festival days, more than 100,000 people visit this temple that is there in this town. But it's also a major education hub with a number of institutions and universities. There are about 6 or 7 universities that are located in and around Tirupati, though it's a small town. So it's a major educational hub. And we also have our Indian Institute of Science Education and Research that is located in Tirupati. So here's an opportunity to work with a lot of institutions. And when we started off, we were trying to identify what should be our thrust areas for research. and academic programs that will address the needs of the country, number one. Number two is also locally relevant in terms of our geographical location, and also be at the cutting edge of international research. So looking at these aspects, we have identified a few thrust areas for our institute. And these include smart infrastructure, and then energy, food technology and precision agriculture, education technologies, and most importantly, the area that is relevant for today's webinar is in the area of materials and manufacturing. So from early on, we have identified materials and manufacturing as one of our thrust areas. And why did we choose this? From various perspectives. One is from a national perspective. You know, in India, though we have a very large economy, ours is a service dominated economy. And on manufacturing front, while we have a vibrant manufacturing industry, but we are not at the international scale, and also does not contribute to the economy as much as is desirable for an economy of our size. For example, manufacturing only contributes to about 15% of our economy. Service sector contributes to more than 55% or so, and the balance goes to agriculture and other areas. And but manufacturing is also one of the biggest employers in the country. And if we are looking at increasing the employment in the country, we need to make the manufacturing sector stronger and grow larger. So that's one thing. As I told, we are looking at from different perspectives. From a national perspective, it is very important that we strengthen the manufacturing base in the country. And for that, obviously, we need to have a very strong manpower that is developed from institutions like ours at the cutting edge technology areas, whether in terms of applying these technologies or in terms of research. And then we also need to have a very strong research base in developing this capability to be internationally competitive. The other thing is our location. Tirupati is located in the state of Andhra Pradesh along the coast, where we have a number of industrial parks and industrial estates that are there around. Within 50 kilometers from us, this huge big private industrial park called Sri City, which has about 150 companies that have established their base there. Very large manufacturing companies like Mondelez, Cadbury's, and then you have manufacturing companies like Alstom, which makes metro trains there. The metro trains to the various metro projects in India, whether it's Chennai, I think in Lucknow, and one more location in India, three metros. Even the Sydney metro supply of the train systems are happening from this particular location. I'm just giving you a few examples. Kobelco has a huge plant there, and there are a number of Japanese manufacturing people who have set up their base there. And also we have this industrial corridor. If you look at Chennai, we are just about 150 kilometers from Chennai, which is one of the biggest industrial cities in the country. So we're very close to that. We're about 250 kilometers from Bangalore. And then, for example, Tirupati has been identified for the electronic manufacturing clusters. The first cluster has already been set up. They're setting up the second cluster, and so on. So there's a huge manufacturing ecosystem that is developing in and around where we are. So we would like to be very much, associated with developing these industries, bringing in new technologies, upgrading technologies, and also be at the cutting edge in terms of research. And we are, as a new institution, we had started off from this, as I told you, in a temporary campus. We are building our main campus on a 548 acres, beautiful piece of land with a mountain backdrop that is under construction. Already, we have set up quite a few labs there. The students' classes happen in our permanent campus. We have set up classrooms. We have the student residential blocks, hostels, where also the students all live on campus. Of course, because of the pandemic, the students most of the classes are still online. So, but we have the students who are doing research, especially who need experimental work, they're all on campus, continuing their work, who are taking care of all the requirements, all the safety precautions and all that in the context of the pandemic. And then we are building out, so we've already built about 30,000 square meters, which is about in India, we talk in terms of lakhs, so about 3 and square feet, over 3 lakh square feet. But now we have under construction, and the work is progressing. We have about 1,500 workers working in our construction site today, where we're building our major department buildings, laboratories, further classrooms, housing for faculty and staff, a large central instrumentation facility, our administrative building, and all this, and the construction is progressing at a very fast pace. And by middle of 2022, this whole campus, this particular part of the campus should be ready, which will house office space for about 100 faculty members and the associated labs with these faculty members. So this is another 130,000 square meters of facility that is getting built. And this is stage 1. And then once we get close to completing this, we'll start our stage 2, which will be doubling this capacity, more than doubling this capacity. So by 2024-25, we've had a full-fledged campus will accommodate about 2,500 students, about 250 faculty members, and all the associated research laboratories and so on. And we have also started various interactions with the universities across the world. We have built a very strong relationship with Texas A&M University in US, especially in the area of manufacturing. I see Dr. Satish Mukapatnam from Texas A&M is one of the speakers. We have had our students going there for internships, and some of our students have gone on to do PhDs there. Right now, they're doing PhD there. So, and similarly, we are building up relationship with various other universities. And recently, we have been starting to expand. Now that we have established ourselves, we have started developing relationship with other universities. So I'm very glad that our colleagues have brought together eminent speakers from various countries, including US. I also see my friend Surya Kaldindi as one of the speakers from Georgia Tech. He was 1 year my junior at IIT Madras. And then we have faculty members from University of Nevada, Reno, Professor Pradeep Menzies, and Professor Nikhil Gupta from New York University, Professor David Field from Washington State University, right? And then from UK, we have Professor Klein, and then also we have Professor Dr. Mike Cotto from UK. So we have speakers from this, and most importantly, what spurred this whole initiative was our desire and our initiative to start building relationships with Finnish universities, Finland. So Ajay, if I recall right, has started this whole initiative, starting to reach out to our colleagues in Finland. So I'm very happy to see colleagues from Finland also participating in this webinar, including Professor Pedro Villacca from Aalto University. I had the opportunity to visit Aalto University about a year and a half back. And then also we have Professor Gaurav Mohanty from Tampere University in Finland. So we have excellent speakers, very eminent speakers, and we look forward from this exchange of from the talks that are going to happen and the discussions that would happen over the next 2 days, today and tomorrow, that we are able to take this further to start joint collaborative research projects, exchange of students, and joint publications that will come along the way. So I'd like to once again congratulate my colleagues for putting together this webinar and bringing in such eminent speakers. And as I told you, that we are a very fast-growing institution, and look forward to establishing this relationships. So thank you very much, and all the best for the webinar over the next 2 days. Thank you.
Yeah, thank you so much, sir. Thank you so much for the inaugural address. And now, dear participants, my colleagues and all, I have already shared the program schedule to all of you, and I hope that you have that with you. So today we have 4 talks. So we have Professor Pedro from Aalto University, Finland. He will be talking about the friction-based welding and processing. And then we have Professor Gaurav Mohanty from Tampere University, Finland. He will be talking about the in situ mechanical testing at small length scales. And then we have Professor Klein from Cambridge University and Dr. Jimmy Campbell from Plastometrics. So they will be talking about the metal plasticity and failure characteristics via iterative FEM modeling of indentation, the PIP methodology. And Professor Surya Kalidindi from Georgia Institute of Technology. So he will be talking about the artificial intelligence based knowledge system for SC-related materials innovation. So total we have 4 talks. And now I will invite Professor Pedro to deliver the lecture. So let me introduce him before he starts. Professor Pedro. Yeah.
And here.
Yeah, thank you. Thank you so much. So let me introduce you. So Professor Pedro is the Associate Professor at Department of Mechanical Engineering at Aalto University, Finland. He is also heading the Advanced Manufacturing and Materials Research Group there. And his main research areas are non-destructive testing, NDT methods, and welding technologies. That includes the solid and fusion state processing of all of engineering materials with conventional and advanced techniques. He is also he is mainly focusing on friction stir welding and friction stir processing. Other research areas include coating and surface processing, additive technology, material science, mechanical design, computational mechanics, and product development. He has supervised many PhD students and more than 50 master students. And now I would like to invite Professor Pedro to start his lecture. Professor Pedro, over to you.
All right, thank you so much. It is a real pleasure and honor. I would say an honor to be here. A pleasure would be to be next to you all there, sharing face to face the pleasure of sharing our knowledge and experiences. But this is what we can do at this moment, and it is a great honor to participate in this event. So I want to start by acknowledging the invitation to the director of IIT Tirupati and the head of the Mechanical Engineering Department. So thank you also to the Dr. Ajay for promoting so actively this event, which I really hope it will reach in successful way all the recipients that we have and they are really, the number is really impressive. So please let me know if my voice or my images, videos, whatever, is not reaching you in the best condition. This is the objective. So as always, do not hesitate in calling for a repetition of some action. So I live in Finland and for about 8 years, and I work as professor in Aalto University. Aalto University lies in an absolutely place in a natural reserve bay, and this green image also contrasts with today's completely white one, with minus, I believe, 13 degrees that we have today. And this fantastic experiencing of different seasons. So Aalto University got the name from a very distinct student, professor, and entrepreneur, architect Alvar Aalto, a big name from Finland, but also from the world. We merged recently, so we, as Aalto University, we have university project that started only 10 years ago, but this is founded on the Technical University of Helsinki, with more than 150 years old, and we merge with the School of Arts and the Business School of Helsinki, and we are now Aalto University, I would say the largest and most important technical university with impressive also impact, world impact in the fields of art and business. So Aalto is our name, and I am the head of the group, of the research group on advanced manufacturing and materials with the acronym AM2. We are one of the 7 research groups in the Department of Mechanical Engineering, and we lie in the School of Engineering. So looking a little more into what we do, this group has 8 professors with some distinctive research actions in additive manufacturing, in casting. I am leading the joining of materials and non-destructive testing, where friction-based solutions are, I would say, an highlight from our university with the world impact, mostly based on the innovations that I will try to address today. The quality control and production management in circular economy, joining closely with the research from material science in hydrogen economy issues, and we are more focused on the side of hydrogen influence in engineering materials and storage, but we have the systems, the energetic systems, and in particular you will see one recent application that we are implementing in using our joining knowledge to produce a new approach for fuel cells. So I look forward, and I understood that this field of energy is also very active at your institute, and I look forward to promote collaborations in this field. So I would like to emphasize also the modeling in multi-scale of several engineering materials with focus on steels. Production of steels is a big issue in Finland, both special steels by SSAB, Rautaruukki before, and stainless steels by Outokumpu. So then, as in all the material science, we invest and we have some distinctive capacity in digital image correlation with algorithms that are unique. And we have also on the level of quality control, reliability and non-destructive testing, some important laboratory installed capacity and research work. So today my talk will be on the solid state welding and processing, with focus on the friction-based processing. And I will start the lesson with 3 leading questions. And this is hopefully the warm-up to get into the perspective over the multiple techniques that I have prepared for the core of the presentation. So we will start define with the definition of the third body region as the domain for the friction-based technology. And then we will go a little bit inside of the friction stir welding and the variants of this welding process, but even more important, the friction stir based innovations that taking advantage of this third body region between the liquid and the solid, the viscoplastic domain, enable us to open and solve several challenges from our society, bringing new products and new materials into the mechanical design and structural performance. So let's start with these 3 leading questions, okay, to addressing the scope of solid state processing within the welding technology. So the first question that I would like to introduce in terms of reflection is why the solid state welding via forging welding, okay, also brazing and soldering existed before, was the only solution for joining metals since the ancient times, so 5,000 years of processing metals since the Bronze Age to the Iron Age, across all the modernity, okay, that encompasses these important steps of industrial revolutions up to the start of 20th century. It was the only solution, okay? And so my question is why nothing else was possible to implement when we have nowadays a large portfolio of solutions for welding the materials. So let's start with the understanding of the perspective of solid state and fusion, where at the start of this recent 20th century, so about 1 century ago, in fact, so we were implementing for the first time, transferring the knowledge that existed in the physics analysis of stable electrical discharge into fusion welding processes, being able to bring high power density into the material. And this shielded metal arc welding supported probably what we had for the good and for the bad, the First and Second World War. And after that period, we have an explosion of solutions supporting the construction, structural construction with submerged arc welding, TIG welding, the MIG-MAG, several variants of these, so, and evolutions. And so this brings, as you can see, an important portfolio of solutions that we live with, and we consider they existed here since ever. Also combustion as a source, relatively high power source compared to everything that existed before for localized heat delivery into the materials. Nowadays, mostly for cutting, brazing, thermal treatment, not so much for welding, as it was overcome by the precision and power density also that we can bring with other solutions such as electron beam welding, probably one of the best overall solutions for joining materials if we don't consider the cost and the setup time inherent to it, and the limitations also in size of components and so on. So Laser more recently brought some freedom into the high power density solutions, covering with several active medias, large spectra of applications. So this is for you to understand that for over 5,000 years, forging was the only one, and only for about 100-year-old we have this large amount of solutions. So what was the problem that was not enabling, even when we had knowledge on electrical arc, to implement it in a stable way? So let's address that. So here you can see, this is a film already of 20th century, early 20th century, okay, 1904 in this situation, but the technology is the same for the technology that was applied. So you see the working machine here is the man. We didn't have a press here, so there is a very professional approach in the plastic deformation. They need heat to reach levels of high plastic deformation and generation of new chemically active surfaces. And you have these conditions of the new chemically active surfaces, the via plastic deformation, the temperature, the compressive load, and the time to activate joining mechanism. So this why was not possible to reach melting in this situation, because initially the power was not enough, and then if you consider the transference of the energetic signal to the material, it overcomes easily the power sources that were available. This means that when you would reach the liquidification in the zone that you wanted to process, to join the materials, to generate complex shapes based on relatively more simple basic raw materials, the amount of processed zone would be too large for the surface tension to address it. So the knowledge here is quite high in physics. The amount of phenomena coupled metallurgically and physically are quite high, and lots of respect for this. And the answer to this question is exactly the fact that there was initially not power sources that were able to reach mostly for iron-based materials, for steels. So there was capacity for cast irons, but for the low carbon level and higher performance, there was some limitations. And when these power sources improved during the time, they didn't have the power density, okay? It was not enough to overcome the effect of heat transport in the metallic components to be joined, okay? Leading to these very large melted zones where the surface tension would not be enough, and we would have a very large, so essentially all the component would be melting upon reaching the melting at the processed zone. So this was the main reason why, before being able to reach controllable high power density sources, solid state was so important, and in fact the only solution. So this brings us, but okay, how does metals get together in solid state? It is relatively intuitive, because we experience with several materials in the liquid phase condition that liquids mostly can mix together, okay, depending on the temperature and some chemical affinity. But we are, in our understanding, two solid bodies cannot exist, and they are stable, and their surfaces are stable, and in fact they are, and that's what enables us to interact with all the media that we have around. So what are the joining mechanisms and necessary physical conditions to activate them? These are the generation of new chemically active surfaces. So you have to break the stable, relatively stable, nothing is absolutely stable in nature or permanently stationary. So everything is evolving. We have to bring new chemically active surface. This means that we have to bring the inside out, looking for new stable interactions with the environment. We have to bring the levels of temperature, which is one of the effects of heat, but not the only one, during some time, and we have to bring these time, temperature, and new chemically active surfaces together under compressive loading. So how to do this? We can generate a liquidification. Yes, there was some interruption. May I continue? I hope so. Let me know if there is any problem from your side. So liquidification and expel out of this surface, liquid surface in flash welding, high frequency welding are good examples of processes that are based on this mechanism to generate new chemically active surface, exposing the internal part by this discarding the liquid. So many times these processes are considered fusion, but they are not, because all the remaining elements when the joining is activated are solid state domain, and the solid state joining mechanisms are activated. And then we have biplastic deformation. Okay, changing the shape means that you have to change typically the surface one way or another, and with flash, as in rotary friction welding, or without flash, as you can have in this autogeneous friction stir welding, or in a localized damage accumulation, as happens in high pressure contact diffusion welding, or damage accumulated in hysteresis cycles in ultrasonic welding. So all these, cleaning is typically not enough, can help enable us to promote new chemically active surface. And I really endorse our researchers to be very active. This is the first element and the key element. And then application of temperature and time controls the type and level of intensity of joining mechanisms, and the compressive load in open die, or for atomic bonding of surfaces, or in closed die condition as you can have in friction stir welding. And these are very similar to the concepts that we heritage from forging welding for this millennium. So what are the joining mechanisms that are activated that enable us to bring this solid state? So between any kind of masses, there are always these attraction of masses relation, and some when we bring them together at very close range, two particles, and they electromagnetic field starts to interact, and they bring this repulsion force builds up. This means that from the attraction side, there is a moment where when we bring the particles together at some close vicinity, the repulsion force and attraction force brings to the system to an equilibrium resultant force of 0. This corresponds to the minimum energy of the system. Fortunately, it means that to come out from this distance which we have in this horizontal axis, the distance between two atomic elements, to come out from this point, you have to apply energy. That is the cutting. This means they are welded. So approximation to interatomic distance of equilibrium or atomic bonding is an important one, mostly when we cannot mix materials together in a bulk state. And this happens by the name of diffusion. We know diffusion for different sizes, significant different sizes of atomic elements, as carbon in an iron matrix, but for similar size of metals with a significant amount of electron cloud, we can have this mixture in a bulk level at the surface, reaching very high performance mechanically if the heat is enough to expand the material and temperature measures exactly this expansion and the vibration state of the surface or the material, and we can activate, in fact, significant levels of diffusion that, after consolidation of the joint at the room temperature, also acts, in fact, as the most important joining mechanism, strongest. And this is, in fact, again, what most of the solid materials are made of. Some mechanical interference also plays a role, and we can call it clinch. So these atomic bonding, diffusion, and some clinching, they all are joining mechanisms for us to use. So at high level of, there is a threshold after which we can change the stable conditions of the energetic position of the surfaces and the materials in the volume, and surface and materials are quite different, although we consider always the same material, but there is a surface engineering that is very relevant aspect of the material performance overall. Above this threshold where no weld exists, when we have more mechanical energy or more heat energy, mechanical generates temperature, but is mostly about the pressure condition or stress condition in the surface. Heat also generates expansion, contraction, so deformation and inherent residual stresses. But the most important aspect is the kinetic energy that we measure as temperature. So at low levels of temperature, we activate mostly atomic bonding. We are not able to go inside with diffusion, which happens for larger amounts of heat. When we have heat and mechanical energy, we have a spectra again of large amount of solutions, activating both diffusion and atomic bonding depending on the energetic conditions that we have. Anyway, within all these domain between the melting temperature and depending on the materials, we can call it relatively cold behavior of the material, we have the viscoplastic domain. So viscoplastic lays in between the liquid domain and the solid domain. It flows essentially as a liquid, but it retains the shear strain capacity and the shape characteristics of a solid. So this is a very important domain, and this is where for 5 millenniums we have been living in, and we are mostly living in this line now, okay, addressing the explosion of solutions above melting with no mechanical energy. There are solutions also here like resistance welding, where we have mechanical energy and melting. And again, that's the reason why resistance welding is so important for automatization and robotization. So the final question is, with so many mature fusion welding based solutions, why are the solid state welding still important and providing some of the most exciting innovations? Okay, so supporting these question is the following slides and talk that I am giving on friction-based welding. So I hope that the next slides enable you to understand this important issue, that why forging, coming from the ancient times, is still nowadays very important, okay? And we have some beautiful statues on forging in the middle of Helsinki that I'm very proud of, that I invite you to come and meet. So let's start with the approach of friction-based technology within this viscoplastic domain or third body region. Friction-based technologies is a tree of encompasses several solutions. There is no classification that is complete, accurate, precise, or even up to date, because as I'm telling, or I wanted to emphasize, there are constant innovations, and we at Aalto University, and I believe at several IIT institutes, we promote this. So today we will see some examples in friction-based extrusion, hydropillar processing. In fact, the first process that I saw when I was learning about friction stir welding, even before it was done in the 90s at the German Institute where I found it, very important place in Europe for that research, Helmholtz-Zentrum Geesthacht. And friction riveting, an innovation that I'm very proud from one of my colleague researchers. I will address it later. Rotary friction welding, a very well established solution with from mid 20th century, so well established. Some particular solutions that are nowadays being implemented in linear welding. Linear welding have approaches that come from the rotary friction, but also approaches that come from friction surfacing, depends. And friction surfacing is quite important because it provides a good solution for thick coating, but more than that, it was the origin or testing on this field that friction stir welding came above, as by our dear colleague Wayne Thomas in the Welding Institute, very creative, intelligent, distinctive person, peer that we have in the world. And friction stir welding has several variants nowadays, but even more important are the new innovations that it opened up. So let's take a look on some of these solutions. Friction extrusion is a method to create a new material out of the swarf flashes coming from different processing, and we can generate, like an extrusion process, a new material, completely sound and solid and coherent in shape. And the friction pillar is a process that I typically take some time with my students when we have this significant amount of lecture time, more than today. Because if you understand how does it work, you really understand a lot about this third body domain. You see some redness coming from this picture. It's just because the radiation emission above 1000 degrees for steels is quite high and there is no melting there. But very important, the viscoplastic domain, the generation of heat, and how it progresses and activates the new chemically active surfaces that with the temperature and the compressive loading generates a consolidated method for filling and very useful for some application. We can even use very useful for some maintenance, repairing. If we find some defect inside of a structure, we can make a hole and then fill it in with forging properties that perform typically at the same or even higher level than the base material that the components are made of. Recently, Sergio Amancio has created this friction riveting, extremely important also because brings one of the answers to the question, why are we still using the solid state? Because we are able to merge metals with polymers, one of the ultimate conditions for joining of materials such as the dissimilarity in physical conditions. So in this process is an amazing phenomenon where the hardness of one and the difference in mechanical properties are brought together to bring the hardness and higher thermal conductivity with a material that is softer and lower thermal conductive as a polymer. Okay, and how this plays these different thermal conductivity, heat generation, and hardness evolutes and how the polymer that is softer becomes harder, stopping the material that is harder originally and becomes softer faster than the polymer due to the thermal conductivity. So really interesting phenomena to study and open up also this possibility for studs inserting in several kinds of components. So friction, another solution for friction-based, sorry. Another solution based on friction in viscoplastic domain is the consolidated rotary friction welding. Friction welding originally, now with the rotary word also to distinct from many others. What you see has not much to do with friction. Yes, initially friction is there to trigger the heat generation. That heat brings the temperature higher, and with the higher temperature, the heel strength comes down, you enable plastic deformation, and then plastic deformation, the dissipation of it during the plastic deformation enable us to reach the new chemically bulk surface. In this situation, we have the material coming out in the form of flash that can be detachable, providing solutions that are applied to several components, from bio implants to automotive, large amount of axisymmetric condition. Typically, this is only feasible for axisymmetric components. There is also the friction linear welding, okay, but this is limited to very low amplitudes, and the field of deformation has to be considered. But a great solution also to bring together materials that are difficult to weld, such as titanium-based components or ultra-strength steels that would lose properties under fusion processing. Friction flow drilling is a magic phenomena to processing large diameter holes, where we can even use the flash as an operative structural part of the component, based again on all these viscoplastic phenomena, very similar to the friction hydropillar, but here in completely open die condition. And then for coating, thick coating, friction surfacing provides a very well known solution, enabling these similar joints. Here we have an austenitic stainless steel, ASI 316, over ultra-strength steel. This was a gift that we provided to our research partners, Rauter Hulki. And we have also implemented studies of additive manufacturing with multi-pass producing rails-shaped components. Although the rough aspect of the open die condition, we really have very sound joining between the layers, and we can use some creativity to generate functionally graded materials, FGM, very appreciated for very dedicated performance, introducing some particles in the mix of the application. Applications to a wide range of materials, including copper and nickel alloys, is one of the most impressive techniques and solutions for thick coating in a large range of materials. So this enabled, it was testing friction surfacing, that friction steel welding came above depositing steel over aluminium substrate, inverting the roles of hardness at room temperature. It is possible to be done, but it is also possible to create something very similar to friction steel welding when you are smart to identify it. So we have at Aalto University created a solution also that can be completely disruptive. Producing tubes and tubular shapes is extremely demanding, and we are now able to produce them without any dyes, in absolutely open dye condition, as you can see in this film. Okay, we can produce canisters, we can produce tubes of variable thickness and variable shape in titanium, and this is by using the self-imposed physical boundary conditions and the buckling phenomena that when flash comes out and changes the flow from horizontal to vertical directions in this axial plan, and taking advantage of the viscoplasticity, we can really change from original basic rods into complex, valuable engineering shapes. So this was an innovation, a very recent one from Aalto University. There are not even publications on that, so you are seeing that in one of the first hands. And we can see here friction stir welding. This one coming, as I told you, from the concepts and some mishaps in the testing of friction surface. So we have a non-consumable tool that is going to process in closed die forging condition. Closed die is dominated by an anvil or another bobbin shoulder in the opposite side of the application of the source of the mechanical energy. We have the cold material in elastoplastic domain, and we have the shoulder on the top surface being processed. The material flow and is stirred together, generating the heat by plastic deformation mostly, and activating with an absolutely chaotic new chemically active condition with the temperature during the processing time under forging condition. We have the final joint. This is a big jump, as you can consider, because for the first time it was possible to address components of complex shapes in linear joints, just like it was possible to be done with most of the power sources for fusion welding. And this was the big jump here. We came from the rotary friction to a very large field of applications. And this process have very peculiar phenomena. Modeling is very easily found to be the approach to modeling, and the phenomena very easily found to be completely wrong. It's not a stationary process at all. We have the steering effect as a period. All the phenomena is periodic, but even not stable, and that non-stability is what enables us to mix the material, providing a sound joint. We have a three-dimensional flow with couple heat generation, so it's not possible to model heat and material flow differently. And many times they're addressed as onion rings, as this dynamically crystallized zone is generated wrongly, because this, as you can see, it's most about a Swiss three-dimensional roll. And so it's very important that most of the perspectives are cross-sections to evaluate the processor, thermomechanical processed zone, heat affected zone, and so on. But as you can see, and you consider that this cross-section is the same along the weld, and it is not. As you can see, in a longitudinal, you have from the start to the end quite different conditions across. So it's an intrinsically three-dimensional phenomena that you need to consider. It is time to stop the very wrong approaches that we have. There is no stable absolute process in welding, but this is definitely, by the nature, it cannot be a stable stationary process. So, okay, I have shown this linear approach. Clamping and the condition, the geometrical condition is always plays a very important role, but we can address with some creativity complex shapes, although with lower flexibility than for electric arc based power sources. But we can really address overlap, U shapes, L shapes, T shapes, produce closed boxes, as you can see here, or even use the great properties for high extrudability here explored with single point incremental forming. Applications to these similar physical conditions is one of the most important answers to the question, why are these processes still so important and opening up doors for bringing new materials together, optimizing their performance. This is exactly what happens in bus bars applications, where most of the copper components have to interact, if they interact at the bolted zones with aluminum components that are lighter and provide a cost-efficient solution. We have several problems on maintenance and reliability of the operation. So it would be important to have a body of aluminum and the tips of the bus bars in copper to interact with all the remaining copper components. But for that, the strength and electrical properties of the weld would have to be reliable. We have implemented that. We have shown the conditions for reaching that in cooperation also with the Indian School of Mines. I hope I'm not saying wrongly, and Professor Somnath collaboration in some of these studies. We share Sashindra and some other students as our doctoral students, and in our group we have several members from Indian scientific society. I have a postdoc working with me, some other students from original Indian education, great researchers, great people, and it's an honor for me to have these collaborations. But coming back to the implementation and scientific properties, we found that in the highest compressive load, the resistance that exists between aluminum and copper is about 200 times higher electrical resistance than in a friction stir welding, where we got about 50 micro ohms, and we have over 100 for contact resistance at about 4 tons of load for the components that you can see here. So extremely important field of manufacturing that enables optimized performance also in this field. Another completely different application, amazing, a milestone in the world where Finland is ahead. This has been developed between Finland and Sweden by the authorities on nuclear fuel waste management. I cannot disclose too much here, but I can say that friction stir welding and electron beam welding were the last processes used to produce welds in very thick copper canisters that provide the corrosion resistance to store the radioactive pellets that are inserted in a cast iron protective layer. And then for corrosion and creep performance, we have the copper layer. 50 millimeters deep welding for closing the cover with the cylinder. And this is done in one pass of orbital friction stir welding. Only possible to reach such a level with the best process there is in fusion welding in absolute terms, that is the electron beam welding. But friction stir welding provided better conditions with a small grain for non-destructive inspection, mostly based on ultrasonic phenomena. The metallurgical conditions provide less loss of the ultrasonic energy, and so not only a reliable joint, but also possible to have reliable analysis of the quality and control. Friction stir welding nowadays also covers possibilities of welding materials like steel, but not for common structural steels. They have very good solutions in fusion welding, but for ultra high strength steels and very special condition steels that we don't destroy the conditions by melting them, we can provide in friction stir welding very reliable and high performance conditions in fatigue and toughness. We are absolutely champions, and welding steel is going to be the big step for friction stir welding. Not steels, but special steels, the ones that don't have good weldability with the existing and important fusion welding process. So on top of that, Aalto has made some important strides in this field we are able to monitor the temperature of the magnetic field. Maybe for the first time, and we have a report in scientific reports from Nature publication on this, we are able to evaluate internal energy of the material. So going to some of the variants, we can have bobbin tool for welding with no access to the opposite side of the weld. We can have stationary shoulder. I'm lost in time. I think I will have 2-3 months. Okay, I'm sorry. We have variants, important stationary shoulder is an tremendous important solution for complex shapes, but also providing great finishing. And we get phenomena like same temperature in the processed zone. So it means that there is no friction coming, heat generation from the friction from the shoulder. The temperature has to be the same for the material to flow. And this is extremely important. Solutions providing larger processed zone are RAS steer by TWI, skew steer, also COM steer. They enlarge the processed zone, okay, with some creativity in the application of the tooling over the material. And we can also have, for more uniform conditions, the re-steer, where the tool rotates in opposite directions, changing from 10 to 10 revolutions, and providing a more uniform field. We can also have different rotations of the shoulder and the probe with dual rotation. And in twin steer, double tooling can enlarge the processed zone, but also can compensate the forces in a way and provide two constraint points that enable us to let go some of the demanding clamping in this process. So, friction steer-based innovations encompass processing of casting, powder materials, enabling superplasticity, processing of base material. The benefits of friction stir welding was so great that we brought this into raw base materials, calling it friction stir processing, with some creativity also enabling functionally graded materials in inserting particles in the mix of the processed zone. Aalto brought some important innovations that started in the United States with friction stir channeling, where we can produce subsurface channels that can go in any direction with very significant roughness and high internal pressure strength. And this provides a new field. But Aalto brought a hybrid channeling, where we bring together multiple materials in a weld and channeled processed zone, encompassing a new phenomena. Just like in hybrid laser, you have the integration of a high penetrant power density beam with the bridging capacity of TIG or MIG processes. We also provide here the best of the joining and processed zone with the ability to provide this channel. You can see in this film some applications that we have envisaged recently. Here is for thermal management of batteries with hybrid channel. We merge aluminum plates with an aluminum with a copper component. Basically, the copper produces the thermal management, and the aluminum produces the copper plate produces the thermal management of the components targeted, and the aluminum provides the thermal management of the copper. So we have the high performance copper with the low thickness and low price for that reason. And here you can see the channel in the aluminum. to the copper, the implementation in automotive industry. This is the top and bottom. In the middle, you have the battery pack. And this encompasses multiple battery packs already. The holes that you see already were, so this was the implementation in a company, RetroEV, partner from us in this study. And the implementation of transforming classic cars into electrical vehicles with the hybrid chain solutions integrated. So I will skip some of these. I want to emphasize, because I believe that I'm quite in the middle, in the end of my presentation. I want just emphasize and also a new evolution from these solid state processing provided by Aalto University, where we have for the first time capacity to produce linear joints between metal and polymer. Okay, this is now being implemented in production of or tentative production of fuel cells. Okay, you can see a sandwich here produced with the through-hole extrusion welding, some cross tension and tensile shears here implemented, showing the toughness and strength that we can reach with these absolutely different world materials in terms of engineering performance. Okay, I close my presentation. Sorry for being so long. I believe that I should be at the end of my time. So with some final remarks. So these techniques based on solid state welding and processing are in permanent advance since many centuries ago, resulting in a wide range of solutions from mature to modern breakthroughs, including some of the most impacting innovations in the world wonderful of welding, where friction stir innovations encompassing friction stir welding are some of these examples. So I'm not sure about the time. I'm lost in that. I'm sorry, but I came to the end. So thank you very much for bearing my presentation, and I hope you have somewhat been touched by the capacities of innovations that we provide, and we are in contact for further exploration of these. Thank you very much.
Thank you so much. Thank you so much, Professor Pedro. It was really a wonderful talk, and you have shared the fundamentals and advanced findings in the area of friction-based processing and solid-state processing. Now, I request all the participants, if they have any doubt or any questions to ask, they can raise their hands or they can post their questions, or they can ask questions directly.
Good evening, sir. I have a question.
Yes, please, Deepayan, please go ahead.
Sir, what is the significance of thermomechanical affected zone and how it is differed from heat affected zone? And is it applicable only for fixed star welding?
No. As you have let me, okay, I will try to express this without the support of slides, but we can take more time than in a private talk. But so as you understood, or I tried to mention, you need this thermomechanical processing. So the heat affected zones from thermomechanical processing are typically relatively small, but the amount of heat that heat, in fact, that flows to the heat affected zone is relatively small. It doesn't mean that the amount of energy, because you use mechanical and heat energy in all these processes, okay? It doesn't mean that the amount of energy is smaller. So in friction stir welding, it is wrongly mentioned many times in publications that is a low heat input process. No, it is a low peak temperature process, but the heat input that flows to the heat affected zone is small, but because most of the energy is consumed in the processed zone. But the process really requires a significant amount of energy because the volume of processed zone is large. So you have this thermomechanical processed zone that inside you can have dynamic recrystallized zones or not, depending on how the material nature, microstructural nature behaves with the thermomechanical processing. So you always have in this process thermomechanical processed zone with distinguishable features, and then you have some flow of the energy into the heat affected zone. This heat affected zone experiences much lower temperatures than the heat affected zone that comes from fusion welding, okay? Because obviously that the limit of the peak temperature is lower. But the amount of energy that is consumed is not lower, but definitely not with laser and electron beam has much less energy because the volume process per volume, that is true. The amount of energy is smaller, but the absolute energy in these processes is typically higher. But the benefit is the safety and the environmental impact that we have in bringing these two materials together during operation with no fumes emission, typically very friendly of the safety and of the environment. But most important is the performance of these structures that optimizing materials enables in our society later on. That is the real benefit for society.
And sir, what grain structure will be different? No?
Sorry, I didn't understand.
The grain structure will differ in these two zones.
Oh yes, we are speaking always in different animals. We need to address if it is a steel, if it is an aluminium, if it is a polymer, if it is a composite. Okay, what are we talking? We can go for all of these materials. So we have to address specific issues with a specific case study. Okay. Microstructure is quite the main idea is that we preserve the original properties of the base material with these techniques more than with alternative fusion welding, and in some materials, depending on how they are manufactured, we can even provide better performance than the base material. Okay, because the base materials typically, when we speak about the most used ones, aluminum alloys, steels, stainless steel, they are thermomechanically processed to reach this very high performance that is not possible to reach with additive manufacturing or with casting. And we have a solution that is exactly in the same nature.
Yes, sir. Thank you, sir. Thank you very much.
Thank you so much. Any other question? Any other question from any participant?
In fact, we all learn more with the questions and answers than with the presentations. This is my belief.
Sir, I have another question, sir.
Very good.
Okay.
Sir,
Thank you.
Sir, can we convert a vertical milling machine into a friction stir welding machine? And how?
Yeah, you need to control what you are doing, and this is absolutely important. Okay, because you can only because there are parameters such as the position of the tool, which a milling machine can provide, but there are other, and the rotation and travel, but there are other parameters such as the loading condition, the torque, the forging loading, but also the temperature in the surface, also inside, that we need to monitor. So yes, for sure, a milling machine is the heart of the friction stir welding, but we have other machines for ultrasonic processing, for many other processes. So any source can be used anyway here, but we need this encompassment of mechanical and heat sources. But your creativity and knowledge is the only limitations for further steps for friction stir welding in particular. I want to emphasize that more important than friction stir welding are all the new things that we can do with the knowledge of friction stir welding.
Okay, sir. Thank you very
Thank you
much.
for your very good questions and comments.
Good afternoon, sir.
Yes, hello.
Yeah.
Yes, sir. I have a question that what are the properties that we have to choose when we are going for the FSP? Like when we are going for the FSW, that time we are finding out the tensile strength and other things. But for the FSP, what are the properties that are required?
The question is, why are you doing FSP? So those are the properties that you are looking. So why you don't do something just, okay, in research we do that. We like to do things because we always learn, and learning is... Sorry, any, may I continue?
కృష్ణ సార్ కింద ఉన్నాడు కృష్ణ సార్ ఉన్నాడు మీకు ఫోన్ చేసినప్పుడు ఉన్నాడు సార్ అక్కడ
Doctor, yeah, Ajay, may I continue with the answer, or?
Please go ahead. So he's asking this,
Yes.
what are the important parameters, properties we select while doing the FSP?
Yeah, I believe that the question was on friction stir processing, correct?
Yeah.
Yeah, FSP. So the performance of FSP, it depends. Are we doing FSP on a raw material that comes from a forging operation, a steel plate, or are we doing, as an example, or an aluminium plate, or are we doing it in a casted component or in an additive manufactured component? So we can do FSP for improving locally, for removing defects. We can do FSP for improving metallurgical properties of hardness, toughness by the grain size that we can bring the materials into. We can, in fact, apply some functionally graded properties by mixing materials together. So FSP is different from friction stir welding, because in friction stir welding you have oxide layers in the joint zone. In FSP you have just superficial stable layer. I'm calling oxide, but it's more than oxides. Okay, there are several passive elements for forming the surface. But so welding is more challenging from the sound perspective. But friction stir processing has another problem, as one problem. In welding, you are already providing a service that is merging the materials together. In friction stir processing, you are destroying to bring some better properties afterwards. So you have to balance this very carefully. Okay, it's a good solution, but very expensive to do it. So you need to be careful if the benefits are really in balance with the price of doing it, from the risk that we do when we are applying already to a component that has a value in itself, coming from a casted component. And you always have this start and end of the processing that are critical. By the whole left, when the tool comes out, there are techniques to solve that. But the start definitely is different from the progressed zone. And as you have seen, it's not absolutely stable. All these can be brought into benefit, but you have to understand what you are doing.
Right. Thank you, sir.
Thank you. Thank you so much, Professor Pedro. I think you have spent sufficient time with us. It was nice having you here. And thank you once again for giving a very nice talk and information about the solid state processing, especially on FSW and FSP, and answered all the questions by the participant. Thank you, Professor Pedro. Thank you for joining. Yeah.
Bye-bye.
Yeah, now we have next talk. We have Professor Gaurav Mohanty from Tampere University, Finland. Professor Gaurav.
Hello, hi.
Yeah, okay,
Hello,
thank you so much. I hope you are there. Okay.
Yes.
So let me introduce you briefly. So Professor Gaurav Mohanty is the assistant professor at Tampere University in Finland, and he is working on studying the deformation behavior of materials at micro and nanometer length scales using in situ micromechanical testing inside the scanning electron microscope. And he uses the focused ion beam, F5E, to mill the micro specimens like micro plugs for compression and micro cantilevers for fracture testing, and study their mechanical properties over the wide range of test conditions, and that may be cryogenic to ultra high temperatures from -150 to 1000 Celsius and at higher strain rates. Okay. He is also developing novel experimental techniques that enable performing time-dependent transient and high cycle fatigue tests at small length scales. And his group explores the temperature and strain rate effects in materials ranging from metals, alloys, semiconductors, ceramics to thin film and coatings. So now I would like to request Professor Gaurav Mohanty to take over and deliver the lecture. Professor Gaurav Mohanty.
Thank you very much, Professor Ajay. First of all, thanks to you and the organizing team for putting together this very nice international webinar and for giving me this opportunity to present my research in front of all of you. And a very warm afternoon to everyone there in India. So I'm very delighted to be presenting my research in front of all of you. So I am Gaurav Mohanty, and I'm an assistant professor in Tampere University in the Department of Engineering Materials Science. And my work is on studying the mechanical properties of materials, particularly at small length scales. By small length scales, I'm typically referring to micrometer length scales. So I'm going to, through the course of this presentation, I'm going to explain, in situ mechanical testing to you about the length scales at which we measure these mechanical properties. And for those of you who are wondering where Tampere is or where Finland is, I've also got some couple of slides to introduce the place to you as well. So here's a brief overview of the talk which I'm going to present today. I'm going to start off very light by showing you some slides about Finland, about Tampere, and about my research group. And then, because Ajay told me that there'll be a lot of students here, I thought it's important to put in some slides on introduction that will introduce micromechanics research to all of you, and particularly the students who are attending this talk. Afterwards, I'm going to move on to presenting to you one case study of applying micromechanics research to solve a problem in artificial dental materials or processes comprising of zirconia and porcelain interfaces. Then I'm going to move on to just give you a flavor of advanced in situ mechanical testing that not only combine electron microscope and mechanical testers, but also combine electron backscatter diffraction and synchrotron X-rays. And finally, I'm going to end this talk by presenting in front of you the transient testing techniques which we have been developing in our group that allow us to study strain rate sensitivity and stress relaxation at small length scales. So where is Finland, right? So Finland is a Nordic country in Europe. So by Nordic means north in many of the European languages, particularly the Germanic languages. And the country in red that you see here is Finland. So it is well above, it's pretty much north of Europe. And Finland is both a member of European Union, and it also uses euro as a currency. So it is pretty much a part of the European Union. Although you may think that it is located really north of the other countries of Europe and it borders Russia, it is very well integrated with the rest of Europe. So Finland is also known as the land of 1,000 lakes. To be precise, there are 187,888 large lakes. Then of course there are much smaller lakes as well. So Finland has one of the highest amounts of fresh water available to a country as a function of its area. So you'll find pristine lakes all over the country and beautiful landscapes created by these lakes. It is also known as the land of the saunas. So sauna is the only Finnish word that has made it into the English lexicon. Because of the winters here in Finland, the Finnish were, very ingenious to develop saunas that helps them cope with the winter, and it adds a lot of refreshment, particularly in the cool climate. Saunas are taking over all over the world now. You can find saunas in pretty much in all parts of the world and all hotels and spas. Another lesser known fact about Finland is it has the highest percentage of forest cover in Europe. So it's a very green country. It offers you lots and lots of hiking and nature related activities, both in summers and in winters. And speaking of winters, Finland does receive a lot of snow. When it turns into majestic winter wonderland, right? It creates these amazing landscapes. And if you travel a little bit further north of Finland, inside the Arctic Circle, then you will be able to glimpse the Northern Lights or the Aurora Borealis that creates these amazing greenish hues in the sky. So Finland has also been consistently ranked as the happiest country in the world by the United Nations World Happiness Report survey. Now, what this survey has tried to do is it has looked at the socioeconomic factors that allow the people to lead a more prosperous and enriching life. It has to do a lot with social security. It has to do a lot with the standard of living, with whether people are happy with their governments or not. It has got to do a lot with how efficient the government machinery is, very low levels of corruption. So combine everything together along with the pristine nature and everything that Finland has to offer. No wonder that the Finnish consider Finland to be one of the happiest countries in the world, and in fact, it consistently ranks in the top when it comes to ranking of countries based on happiness. Well, Finland is a very small country, right, and tucked away in the northern part of Europe, but you'll be surprised by the amount of impact that Finland has had at the global scale. Probably all of you are aware of the mobile communication company Nokia that pioneered the mobile revolution. 15 years back, 20 years back, Nokia handsets were the only ones pretty much that everyone was buying, even back in India and all over the world. In fact, many of you might already know this game Angry Birds that became a craze all over the world. This came out of a mobile gaming company called Rovio. Then you'd be surprised to know that Linux, the open source platform, was developed in Finland. In fact, it started off as a project at University of Helsinki and eventually became the Linux operating system. Now, Polar probably may be a lesser known company in India, but people who are into wearing wearable devices, they may already know this name. So Polar pioneered heart rate monitors. In fact, they developed the first heart rate monitors in the world, and they were primarily developed for Finnish athletes to measure their performance, to evaluate the performance, when they were going for international competitions. And since then, Polar and other companies have made a lot of strides, and now they're offering these wearable gadgets that can record your heart rates. You'd also be surprised to know that the first GUI-based web browser was made in Finland, and also that Nokia was the first company in the world to start offering its customers the ability to to send messages, or SMS, short messaging service as we know it. So Finland, as you can see, has been a very exciting place for someone who wants to be in the technological domain, who wants to do research, wants to do applied sciences and applied engineering, particularly, that make an impact in everyone's life. And for particularly the material scientists out there, you may know that atomic layer deposition was also developed here in Finland in University of Helsinki. So it's a thin film deposition technique that allows you to deposit monolayer by monolayer, one monolayer at a time, very precisely on a substrate. So the bottom line I want to make here is, Finland has this huge technological ecosystem that not only supports basic research, but it also supports a lot of entrepreneurship. It supports coming up with a lot of cutting edge technologies at the same time. So now the second missing thing is, where is Tampere, right? So Tampere is a small city that is 180 kilometers north of Helsinki. So this is Finland. Helsinki is on the coast. It's and across the strait you can see Tallinn, Estonia. So if you travel north by for 2 hours, you will reach Tampere. Now Tampere is the most populous Finnish city after the greater Helsinki area. In fact, amongst the Nordic countries, which are the Norway, Sweden, and Finland, Tampere is the most populous inland Nordic city in this region. It is a major urban, economic, and cultural hub for central Finland. As you can see, this is the urban area in light white, of Tampere, and Tampere is pretty much perched very nicely between 2 big lakes, the Nasarjärvi and the Pohjärvi. It has an urban population of roughly 330,000 inhabitants. And a fun fact, since Nokia, Nokia company essentially is named after the town of Nokia that is located 15 kilometers west of Tampere, right? So Nokia started off as a company, long before the mobile technology came into being. They were into dealing with rubbers and many other products, right? And they have a very long history, but this is the place where it all started from. So I'm a part of Tampere University. So Tampere University is located in the city of Tampere across 3 different campuses. It has more than 20,000 students. It has thousands of researchers. So it has a very active and vibrant research and technological ecosystem in Tampere. So my group, which is the Tampere Micromechanics group, currently comprised of 4 PhD students. 2 of them, you can see them in the picture. Actually, the other 2 students have been recently admitted, and they will join in the next 1 or 2 months. Since we deal a lot with mechanical testing and electron microscopy, we are located inside the Tampere Microscopy Center ecosystem. We have our own alumnus in situ SEM nanoinventor, and in situ nanoinventor is a very compact nanoinventor. As you can see in this picture, the small nanoinventor pretty much fits in the palm of your hand. So, and this nanoinventor goes inside the scanning electron microscope chamber, and it allows you to perform the mechanical testing and simultaneously view the deformed area using the electrons in the SEM, right? So, and we also have our own dedicated SEM for in situ mechanical studies. That way we don't have to fight with other electron microscope scopes for space, which is always a concern in bigger microscopy centers. And the Tampere Microscopy Center comprises of, apart from many SEMs, it comprises of a focused ion beam, TEM, AFM, XRF, and so on. And because we are also part of the engineering material science department, we have access to a host of other experimental facilities through Material Science Network. So this was just a very brief introduction of where we are, and how we are located. So now let's move to the main topic of this talk, small-scale mechanical testing. Now, mechanical testing has been around for hundreds of years, right? And you may ask, why do we need to perform mechanical testing at small length scales? Well, because of advances in materials processing technology and in the different kinds of materials that we use in different domains, there has been rapid miniaturization of materials. These have been in the form of thin films that are ubiquitous everywhere. These are in the form of MEMS devices, microelectromechanical devices that are really small, right? For instance, here you can see a MEMS device, right? Which has a small component here, and this entire MEMS device is even smaller than 1 cent coin, right? So thanks to this miniaturization, now you can carry a phone in your pocket, right? And you have access to all the information in the world at your fingertips. Then not only for electronics, but MEMS devices or microcomponents are also used in many mechanical devices. For instance, the Swiss watches are probably one of the very well-known examples, right? The Swiss watches are known for, having, hundreds and thousands of mechanical components that work in sync with each other, right? And provide you a very accurate time. So here's an example of a microcomponent from a Swiss watch. And you can see that this is even smaller or roughly the same size as the head of your matchstick. So now when you have these very small, samples or small applications, materials, it becomes necessary to be able to test their mechanical reliability, performance, and properties at very small length scales. Then small scale mechanical testing is also driven by certain applications. For instance, in nuclear reactors, when materials are getting exposed to radiations, then typically the irradiated material damage top layer is a couple of micrometers in depth, and it becomes very important to quantify and measure these mechanical properties very accurately, and this can have very far-reaching significance, right? For instance, particularly for nuclear materials, you want to be absolutely sure of the mechanical properties so they can model and increase the safety of the nuclear reactors. Now, miniaturization and testing materials at small length scales is not the only driving factor for small scale mechanical testing. Even though you have these traditional bulk materials, you will still need small scale mechanical testing. So for those of you who are metallurgists, right? So metals or composites, each material can comprise of multiple grains, multiple phases. Each of these grains, can have different orientations. And if you have anisotropy in mechanical properties, which means that, the mechanical properties of the grains depend on their orientation, right? Then it becomes very important to, quantify and assess the mechanical properties, the mechanical anisotropy. So when we do the bulk mechanical test, we often get an averaged mechanical property data. But if you're able to miniaturize the test, and for instance, here you can go out and map out the mechanical properties of each of the individual grains in this material, then you will know the mechanical anisotropy, and you'll be able to pool in all of that information together in for simulations in order to come up with materials that have better mechanical properties. For instance, if you know that certain orientations, which orientations, which phases provide you better hardness, better elastic moduli, creep resistance, and so on, then once you figure that out, then you can preferentially use that information to generate microstructures that have better mechanical properties, and then use that knowledge to fine-tune your material processing conditions so that you get the desired microstructure. And finally, when we start miniaturizing materials to small length scales, their mechanical properties are not the same that you see them at the larger length scales, right? And this is termed as size effects. Typically in metals, when you are testing them at micrometer length scales, you may get higher yield strength or other mechanical properties that are different from what you would have expected from the same material if you would have tested it at millimeter or even centimeter length scales. And that also is one of the main driving forces for this type of research. Now, nanoindentation is the technique of choice for studying mechanical properties at small length scales. Now, nanoindentation, as the name suggests, it's indentation performed at nanometer and micrometer length scales, right? So nanoindentation is an instrumented indentation technique in which, as you can see a tip here that is indenting onto a material here. So as you're indenting into the material and as you unload the indenter, you're continuously recording the load and displacement at very high frequencies. So, and also the load and displacement are measured in very fine resolution. For instance, the load is measured in micronewtons and the displacement can be measured in even sub-nanometer resolutions. So this provides you a very high mechanical spectroscopy data, like a load displacement curve, where you have a loading segment and you have an unloading segment. Now, of course, as we have known for hundreds of years, is if you take the maximum load and divide it by the cross-sectional area, you can get the hardness of the material. But the interesting fact about nanoindentation is, as you're unloading it, and if the unloading is purely elastic, then you can use the slope of the unloading curve and then use contact mechanics solutions to predict, to determine the elastic modulus of the material that you're testing from the unloading stiffness that you get from your measurements. So nanoindentation has been around for around 30 years by now, and you can find hundreds and hundreds of papers published every year by various research groups that use nanoindentation to calculate modulus and hardness of, I don't think, I cannot think of any material class that has not been studied with nanoindentation as of yet. In fact, nanoindentation has become so routine that nowadays most of the material science departments or metallurgy departments have their own nanoindenters. So now, so I'm not going to dwell so much into measuring the elastic modulus and hardness using nanoindentation, but I'm going to move a bit ahead, which is how do we measure other mechanical properties using in situ nanoindentation. Now, as you are only limited by your imagination in terms of the mechanical tests that you can miniaturize. So any mechanical test that you can perform at the bulk scale, as soon as you can figure out how to prepare those specimens at micrometer length scales, then you can perform those tests at small length scales. Now, of course, focused ion beam is a technique of choice for us to go to, where we used fibs that typically have gallium ions to mill out very small, fine micro architectures. For instance, you can use a fib to make small pillars, right, or columns. Typically these columns are 1 to 2 micrometers in diameter, couple of micrometers in height. You can use the same technique to mill out small cantilevers, for instance, right? You can make even double cantilever beams using the same technique. So, and as soon as you have figured out how to miniaturize these specimens, then using a nanoindenter, and you can change the tip from a sharp pyramidal tip, which is often used for nanoindentation, to maybe a flat punch, a conospherical tip, depending on the test that you're doing, and then you can perform any of these tests. So we typically do these tests inside a scanning electron microscope. So just to give you a list of the different tests that can be done, a small subset, of course, we can do indentation. We can perform micropillar compression. So micropillar compression is a uniaxial compression technique, where if you know the initial height of the pillar, you know the diameter of the pillar or the cross-section area of the pillar, right? And a nanoindenter typically gives you the load and displacement. So you can compute engineering stress strain data in uniaxial compression. You can prepare a small microcantilever, right? And you can push it up and down to perform a very localized fatigue test, for instance. Right now, we are developing a lot of high strain rate techniques where we are performing indentation or micropillar compression, and we are deforming them at a very rapid speed. And we have been able to reach up to 10,000 per second of strain rates, where we are almost getting into the impact regime now. Here's an example of a bending or shear deformation, where you have a pre-milled microcantilever with a notch in there, and we are using a conospherical tip to align it at the center of the cantilever and then push it down to perform a fracture test. Of course, you can take a tip of your choice and you can start scratching onto thin films to look at tribological properties. Here's an example of a double cantilever beam where you have a notch, and as you push this double cantilever beam with a flat punch, then you see a very stable crack propagation, which is very useful for determining fracture toughness. And finally, you can take the same experimental setup, and by oscillating the tip very fast at very high frequencies, you can perform repeated nano-impact tests. And nano-impact tests are extremely useful to assess the adhesion of thin films, or the impact resistance of thin films. So this is what we are playing with in our group, right? So now when it comes to my research on micromechanics, we are doing a lot of in situ testing of different kinds of materials, and we are not only combining them with scanning electron microscope, but many times we do combine them with electron backscatter diffraction, with micro-Raman, and with synchrotron X-rays to understand this, the change in structure of the material as we are deforming it. Because micromechanics is an emerging area of research, there are a lot of groups around the world that work on technique development, because we want to miniaturize the mechanical testing very reliably to measure mechanical properties, right? And as I mentioned, hardness and modulus are pretty well established, but we need a lot of technique development to measure other mechanical properties quite reliably at small length scales. In terms of capabilities, not only can we perform these tests at room temperatures, but we can perform them over a very wide temperature range, going from cryogenic temperatures of -150 degrees to 1000 degrees centigrade. And we can vary the strain rates. We can perform these tests at quasi-static strain rates of 10 to the power -5 to, very high strain rates of 10,000 per second. And our nanometer is also equipped with oscillation capability, where we can oscillate the tip up to 10 kilohertz of oscillation frequencies. So imagine doing fatigue tests at 1 kilohertz or 10 kilohertz oscillation frequencies. That means you can reach the high cycle fatigue regime in a very short duration of time. And we are typically a micromechanics group, so we work with a host of different materials through our collaborators and through the funding that we receive. So we work on metals, semiconductors, ceramics, polymers, glasses, and thin films and coatings. So I'm going to now, after this brief introduction of micromechanics and the various possibilities that we have, I'm going to present to you one case study of artificial dental material, a zirconia porcelain prosthesis. And with this example, I'd like to point out how we can use micromechanics to solve a problem in material manufacturing and reliability, for instance. So artificial dental materials, are typically made of yttria partially stabilized zirconia, right? And so zirconia has very high strength, it has very high toughness, it also has a pretty pleasing aesthetic appearance. These are ceramics that are shaped into the required geometry at 1600 degrees centigrade, very high temperatures. But because it has very high hardness, if you make a dental component out of only YPSZ, it's going to start abrading your natural tooth. So to avoid that, you have to coat the zirconia with layers of porcelain. Doing that, reduces the hardness of the artificial tooth that is going to be used, and that is going to prevent the wear of your existing natural tooth or teeth. And it also has a good aesthetic appearance. And typically this is done in the industry by first, shaping yttria partially stabilized zirconia into the required geometry, and then applying layers and layers of porcelain at 650 degrees centigrade, by a veneering process. Now, this, because you have here a classic example of an interface between two different materials, and particularly coming out of a high temperature processing, that results in a lot of buildup of residual stresses on both the sides and also at the interface. And this typically leads to near interface chipping of porcelain and zirconia, right? So you have a lot of failure in these artificial dental materials. Now, this is something that we wanted to investigate. This is a collaboration with Professor Alexander Korsunsky's group at Oxford University. Now, Professor Korsunsky's group had already done a very systematic study of the microstructure of these artificial dental materials previously. So, so what we did was we took one of these artificial dental tooths, right? And we cut a cross section out of it and we mounted it on a SEM stub. Here you can see that you have YPSZ layer here in light. You have the porcelain layer on top of it, right? And of course you have some polymer mounting to fill up the void, right? And these samples were polished. Now, if you look at the TEM or using transmission electron microscopy of how this interface and near interface region looks like, on the porcelain side, you see a lot of voids, and typically these voids appear because of the buildup of large residual tensile stresses, and these voids form to relieve the residual stresses. On the YPSZ side, here you have the interface and you have a high contrast zone where you can barely make out the grains. So you have to move at least 5 to 7 micrometers away from the interface before you start making out where your typical YPSZ grains are. So there's an example of a very heterogeneous microstructure, so to speak, right? It's not a very homogeneous microstructure in this material, right? And so we decided to look at the fracture toughness variation across this interface. You know, how does the fracture toughness change as you move from porcelain, move towards the interface, and then go towards the YPSZ? So to do that, we took that sample, which I showed you in this image, right? We took this sample, which is polished and mounted, and we put it inside a focused ion beam, FIB-SEM, and we used gallium ions to start milling out, you know, tens of micropillars. Now, these micropillars were milled in such a manner that some of the micropillars were located exactly at the interface, where the interface ran through the center of these micropillars, and then the other micropillars were milled at varying distances from the interface. So on the left, you have porcelain, on the right, you have YPSZ. So a total of 50 micropillars were milled in this region, right? And each of these micropillars had a diameter of 5 micrometers, and they were 5 micrometers tall, and the center to center spacing between the micropillars was around 10 to 15 micrometers. So, and after milling these micropillars, we put a small cross on the top of these micropillars to locate exactly where the center of those micropillars are. Now these crosses were put to very shallow depths so as to not interfere with our fracture toughness tests. And then we took a cube corner tip, which is a 3-sided sharp pyramidal tip, and started indenting into these micropillars. Now, this kind of tests are called the pillar splitting tests, and they were originally developed by Marco Sebastiani from Roma Tre and first reported in PhilMag in 2015. And the idea is you make these pillars, right, that have a height to diameter aspect ratio of 1:1, and you start fracturing them with a sharp tip, right? So now naturally porcelain is highly brittle. It fractures very, fractures almost instantaneously, whereas zirconia shows a little bit of pressure-induced transformation, so it doesn't fracture as neatly. But the idea was we perform these pillar splitting tests on each of these 50 micropillars at varying distances from the interface, and using the formalism developed by Marco Sebastiani and others, we try to calculate an initial estimate of the fracture toughness value, right? Let me point out that by fracture toughness here, this is just an initial estimate. We are not, because the YPSZ does not fracture, it's not fully brittle. So these should just be considered as first estimates. So now after performing these fracture toughness values, we started plotting them on a graph where y-axis is fracture toughness, x-axis is the distance from the interface, 0 is where the interface lie, right? And then you can see that on the YPSZ side, the fracture toughness increases just a little bit within 10 micrometers, and then it pretty much stabilizes to the literature average values. Whereas on the porcelain side, there's a huge drop in fracture toughness within the first 50 micrometers from the interface, right? And the highest drop is seen around 25 micrometers from the interface. The green lines that you see are the literature average values that have been reported for bulk testing or larger lens scale testing than what we are reporting here. And so we had very good match with the literature values for both porcelain and YPSZ away from the interface. Now, the thing I would like to point out is, this huge drop in the fracture toughness very close to the interface, which is within 25 to 30 micrometers from the interface. We suspect this is the main reason why this porcelain YPSZ, dental processes, shows near interface chipping. And this is also correlated with the residual stress measurements performed by Alexander Kosinski's group previously, where they have conclusively shown that there's a huge tensile residual stress on the porcelain side. So now, with this, I just wanted to give you an example and a flavor of, how not only can we use micromechanics, to study small lens scale problems, but also use it as a tool to laterally map out, interfaces and very heterogeneous microstructures that, for example, what you may get from welding processes like Professor Pedro mentioned in the previous talk, or from other joining processes, right? And you can use it to quantitatively map out, for instance, the heat affected zone, the fusion boundaries, or and these and interfaces and near interface affected zones. So now I'd like to move on and give you a very brief overview of other kinds of tests that we can do. So we can do these tests not only inside the SEM and observe the deformation and get the mechanical properties, but we can also combine them with more quantitative techniques that provide you quantitative information about the structural changes occurring in the material. In this case, electron backscatter diffraction. So we took tungsten single crystals as a case study, right, where we milled, tens of these microcantilevers on a single crystal of tungsten. These microcantilevers were, 20 micrometers in length, 5 to 7 micrometers in thickness and width, and they were prepared by focused iron beam again. Some of the cantilevers were left as they were milled, and on the other cantilevers, we put a small notch to mimic a fracture toughness test. And the basic idea was that we align the microcantilever in such a manner on the nanoindentor that sits inside the SEM in such a manner that when we are compressing or pressing down on these microcantilever with a conospherical tip, right, the free end of the microcantilever is facing the EBSG detector. So what we could do is, these are 5 stages of deformation. So stage 1 is before we start compressing it. Stage 2 is in the elastic limit, within the elastic regime. 3 is somewhere in the elastic plastic transition regime. 4 is in the plastic regime, and 5 is after we retract the indentor tip. And the idea was, you go to each of these points and then you hold the displacement constant for 20 to 30 minutes. The time it takes to complete one long EBSD, high resolution EBSD scan on this face of the cantilever, right? And with this, we could obtain information about the structure of the cantilever on the surface. Now, I should point out that EBSD is pretty much a near surface technique, right? You have an interaction volume with the electrons, right? That is typically 1 micrometer in depth, or you can tweak it by playing with SEM parameters. But so we ended up doing a mapping where each of these points of mapping was around 250 to 300 nanometers apart, and we bombarded the entire area, right? Essentially, we ended up taking maps, EBSD maps of the microcantilever. So here's the bending stress displacement diagram. So 1 is, as I told, before starting the measurement. 2 is in the elastic regime. 3 plastic, 4 plastic, 5 is afterwards. And you can clearly see from high resolution EBSD analysis that, how the principal stresses are developing, right, at different stages of deformation of the microcantilever. And you can also, using cross-correlation techniques pioneered by Angus Wilkinson's group at Oxford, you can also calculate the geometrically necessary dislocation densities that you see on the surface of these microcantilevers as you are deforming them, right? So this provides a direct visual information obtained from purely experiments about how the dislocation structure and the elastic stresses are developing in a microcantilever when you perform the microcantilever bend test. And for comparison, of course, we try to compare the unnotched cantilevers and the notched cantilevers, right? And here I'm showing you the geometrically necessary dislocation density in both the cases during those 5 stages of deformation. And you can clearly see the changes in the microstructure, in the evolving microstructure, the dislocations that are generated in both the cases, right? Very clearly. So for instance, here, you can clearly see the crack branching, right? And these are along your slip directions, 110 and 112. And of course, it is very well known that plasticity does influence crack propagation. So this was just, the idea of doing this was to get and, to understand what is happening in fracture toughness test at small length scales. Particularly in material like tungsten that is otherwise brittle, but it does show a little bit of plasticity, particularly at the crack tip, right? And here we have been able to visualize it using experiments. So the basic point I want to make is we can combine micromechanical tests, not only with SEM, but also with, with EBSD, with synchrotron X-rays, for instance, to get quantitative structural information about the material, and then correlate that structural information with the mechanical property results, bending stress, strain diagrams, and so on. So I'll quickly run through this one. Here's another example where we took a bulk metallic glass. We took a thin wall, which was 40 micrometers in diameter, and we performed indentation at the top of the wall. You can see the indentation imprint here, right? And we had the sample at DAISY, the German synchrotron, using a nanofocus beam, right? Where the beam, it was a high energy X-ray, synchrotron X-ray beam, and the beam size was roughly 300 nanometers. And we ended up scanning the area beneath the indenter, right? So basically, this was done in transmission geometry. So let's say here you have the wall, right? You're indenting from the top. You have the beams coming from the bottom and escaping, and you have the detector on this side, right? Like we have shown here, right? This is the indentation direction. And using this, we wanted to visualize the evolving elastic strain fields beneath the indenter tip. And we were successful in doing that in nano indentation on a bulk metallic glass as a reference material. So this is another example. These are simpler examples, but you can imagine that we can now extend these to more complicated materials, more scientifically challenging materials, where we really want to understand how is the deformation proceeding as a function of time or strain in a certain material. So finally, I spoke about technique development. So we have been developing a lot of techniques on measuring transient properties like strain rate sensitivity and stress relaxation properties at small length scales, right? So, now these tests have been done at the bulk scale for a very long time, right? But then how do we adapt these tests to small length scales and reliably measure the strain rate sensitivity and stress relaxation? And the other question that we are asking is, can we really trust the extracted deformation parameters from these micromechanical tests? Because we have an exotic testing technique, we have an emerging testing technique, and it typically becomes a chicken and egg problem, right? Do you see artifacts of measurements just because you're using a new test technique and you don't know how it's going to react or what it's going to show on a material? So that is to solve this issue, we we decided to test nanocrystalline metals. These are typically electrodeposited nanocrystalline nickel from sulfamide baths, and they had a grain size of 30 nanometers, right? And the idea was that even if we are performing a small scale micropillar compression, because the grain size is so small, one pillar that we make, which can be 5 to 10 micrometers in diameter, then that is going to still have millions of grains investigated in that pillar volume. And hence, these materials will not show size effects and will be able to compare the micropillar compression results with the bulk test results. So we electrodeposited very small microtensile bars, right? These bars were typically 300 micrometers in thickness, right? And we performed microtensile tests on them, for instance, strain rate jump tests. And then after the test was done and the sample broke, we took the undeformed gripper section and we put it in a fib and milled out very large pillars, right? On which we can perform now exactly the same identical test that we performed in tension. So here's an example of engineering stress strain data where, on nanocrystalline nickel in red, where we tried to perform a strain rate jump test. We started off at 7 × 10⁻⁴ per second of strain rate, and then we started jumping the strain rates up and down, right, over 3 orders of magnitude. And you can clearly see that when we change the strain rates, the flow stresses start varying. And for control, we have also tested it. We are showing you the results from a single crystal nickel, where no matter how much you vary the strain rate, the flow stress pretty much remains the same, right, which is as expected. So the advantage of doing these in situ testing is, of course, you can visualize the deformation as you're doing the tests. These are screenshots of nanocrystalline nickel and single crystal nickel, tested, when these images were taken at different strain conditions. And nanocrystalline nickel, as expected, because the grains are so fine, you can barely make out any surface features in these SEM images. And it's more homogeneous deformation accommodated by grain boundary sliding. Whereas in single crystal nickel, you can clearly see the slip occurring, right, as you start compressing it further and further. So to cut the long story short, we tried to do one of the first direct comparison of strain rate jump tests. So as I told you, we performed a macro scale tensile strain rate jump test. Then we took the undeformed gripper section and we performed a micropillar strain rate jump test, right? And then we also, we made some pillars, but we also had a lot of free area around where we could use nano indentation, right? Or take a sharp tip and start doing indentation strain rate jump tests by using the protocol given by Verena Meyer in 2011. So, and what we tried to do was we varied the strain rate by roughly the same over 3 orders of magnitude, and we tried to keep the same strain rate values as far as possible, right, in all of these 3 tests. And finally, if you start comparing, we ended up getting the same strain rate sensitivity value, M. We got an M value of 0.018 for micropillar strain rate jump test. We got 0.021 for nano-indentation strain rate jump test, and we got 0.024 for microtensile strain rate jump test. So this very good match between the M values obtained on the same material using 3 different test techniques, helps validate our small scale mechanical test methods. And that provides us a lot of confidence that yes, we can use these tests to study mechanical properties very reliably, at these micro scale, this thing. And additionally, we also looked at the activation volumes, for instance, and we pretty much ended up getting 9 to 10 V-cube for our material. So I will skip a couple of slides now. I mean, we can do these tests as a function of temperatures. We can get activation deformation parameters like activation energies also by varying the tests, right? So, after each test, before and after, and even during the test, we can also have a look at the material surface, right? How it is deforming at the surface features. For instance, in these micropillars, we saw extensive grain boundary sliding on the surfaces, right? That seems to suggest that a grain boundary mediated process. And in the large grains, for instance, you can also see slip steps, right? which is again natural. I should point out that you see much larger grains here on the surface because the grains have grown slightly because of the sieve milling process, but the grain structure is pretty much preserved in the bulk of the pillar, right? So we can trust the micromechanical data. So I think I'm running out of time now. And likewise, we also developed stress relaxation tests that allow us to study stress relaxation properties at very small length scales, right? So I'll move on to the conclusion slide now. So I hope through this talk, I've been able to introduce you to small scale mechanical testing or micromechanics. And I've been able to impress on you that not only can you get, hardness and modulus values, but you can use micromechanical test techniques to get other mechanical properties. And you can also use it to, use the high lateral resolution to interrogate interfaces and boundaries in engineering materials. Now, boundary interface engineering, boundary strengths and so on, these are recurrent themes, no matter which field of material processing we take, whether we take welding process, whether we take additive manufacturing, or any of the other methods. Now, to probe the material deformation structure further, you can also combine it with quantitative techniques like EBSD, X-rays, and micro-Raman tests, so that you can now correlate the evolving structure with the mechanical test property data that you obtain from these very precise and fine tests. And finally, our group and many other groups, you have Professor Klein speaking after me, so all of us are developing newer and newer test techniques that allow us to study a host of different material properties reliably at small length scales. And I believe that all of these efforts combined together, will help us to reach a stage where we can, study any kind of materials, any kind of mechanical properties, and try to solve, the innumerable challenges in material processing and mechanical reliability. With that, I thank you for your patience, and I'm ready to take any questions. Thank you very much. Ajay, I cannot hear you. Sorry.
Yeah, thank you so much. Thank you so much, Professor Gaurav. Now I request all the participants, if they have any special queries, they can ask. Yeah, any question?
Hello, am I audible?
Hello.
Yes.
Yes. This is Rupam Jain from IIT Kanpur,
Yeah.
and so impressive talk, sir. But here you have performed some strain rate jump tests on nano nickel and the single crystal one. So how they are correlated? Basically, when we perform the jump test, basically on a bigger sample, like the normal tensile test, the 20 mm sample, let's say. So there we get some kind of rate sensitivity like 0.002 or 0.002, whatever. So, and then you are doing similar kind of tests in compression mode or tension, the micro tension. So how these values are correlated, and are they very near to each other, or there is something, are we only getting the trend only, or the exact values? That is something I am interested into. Thank you.
Yes, thank you, Rupam. That's a very good question. I guess you're asking the question from a chicken and egg perspective, right? If we are performing these tests at the bulk scale, and if you're performing these tests at micro scale,
yes.
Will the results be different or will they be the same, right?
Yes, yes.
If you take single crystals, then you can get slightly different values in M or activation volume values, right? And that is because of size effects.
Yeah.
So because size effect is a matter of concern, right? And it sort of convolutes with the data at small length scales, so to speak, right? That doesn't allow us to compare directly the small scale testing with the bulk test methods. That is why we chose nanocrystalline nickel. And the idea here was that if the grain size is smaller than your specimen size by at least 1 or 2 orders of magnitude, right, then it is a grain size that controls your deformation. Or in other words, you should get the same strain rate sensitivity in a micropillar strain rate jump test that you'd get even on a bulk strain rate jump test, as long as the grain size remains the same and it's the same material, right? That was the motivation for testing them on nanocrystalline nickel here, right? But if you test them on, let's say, BCC metals or HCP metals that show a lot of strain rate sensitivity, and if you take single crystals, then I'm guessing the results will be different.
Okay. Okay.
Thank you. Thank you, Rupam, and thank you. Any other question?
May I ask one more question if you allow me?
Yes, yes, please.
Yes. So the jump test what we are performing are basically the micro pillar test or compressed in the microscope. So many of times I have seen people doing this thing, the stress strain correlation using spherical nano indentation and drawing stress strain relationship from there. So doing the micro compression is obviously the most reliable thing, because ultimately we are doing the compression. But how reliable are those spherical and in contrast to these tests? That is another thing I wanted to, because doing spherical and jump is more accessible to us rather than getting these FIB milled compression tests. Thank you, sir. If you can help us doing that.
Yes. Again, a very good question. So when you do a strain rate jump test or any, you use any indentation technique, whether you're doing it with a pyramidal tip or spherical tip or any other kind of tip shape, right? You have a stress strain gradient beneath your indented tip, right? So you have different, the material in the indentation volume is under different stress levels and strain levels, right? And that has to be very carefully accounted for if you want to get any mechanical property reliably out of it, right? But the advantage of strain rate jump test is that, you are at the end of the day, you're calculating an M value, which is, your difference in your stress state by the difference in your strain rate, right? So, so even if you have, let's say, some errors in estimating your stress values accurately or even your strain rate values accurately, you can still get away with it because it is differential log of stress.
Yeah,
and
ultimately a ratio is there.
Yes, the ratio is there. That is why, previous work by Verena Meyer and others have shown that it is possible to pretty accurately get, even strain rate jump test values from nano indentation with a pyramidal tip also, right? So what I will recommend for your spherical tests is that do a very accurate tip A calibration, right? And the more control you have in maintaining the strain rate constant, right? Or the more control you have in, exactly knowing the strain rates that you're jumping over, right? That will provide you a pretty reasonable M value, in my opinion. So you can check up the work of Verena Meyer. I think, if I'm not mistaken, they have also reported on performing reliable strain rate jump tests using spherical tips.
Yes, sir. Yes, sir. Sure.
If you send me a message, I can send you the paper.
Yeah, sure. I will try to find that. If I didn't get, then I will surely be contacting you. Thank you, sir. Thank you very much.
Yeah. Thank you, Rupam. Yeah. Any other question? Yeah. So if there is no more question, then let us thank Professor Gaurav Mohanty. And it was really a very insightful talk. He covered the micropillar compression surface deformation features at small scale testing. And it was really a very useful talk for all of you, especially who is doing research in this area. Yeah. So thank you, Professor Gaurav. We will stay connected and interact later on. And thank you once again for your time and for your talk. Thank you.
Thank you. Thank you very much.
So, so now we have a break for 1 hour, and we will be meeting again by 4:30. And after this break, we will have two eminent speakers, Professor Klein from Cambridge University and Professor Surya Kalgindi from Georgia Institute of Technology. So we will continue this after the break. So please rejoin again at 4:30. Thank you.
రాత్రి 10:45 వచ్చి రెస్పాన్స్ వచ్చి చాలా బాగుండాలి అందరికి లైఫ్ వస్తుంది సో అది మీరు
everyone. Good evening, everyone. So we will be starting shortly. We have Professor T.W. Klein with us today and Dr. Jimmy Campbell from UK. Professor Klein, are you there? Can you hear us?
Right. Can you hear us?
Yes, Professor Klein, this is Ajay. Can you hear us?
Yeah, we can hear you, AJ. Yep.
Yeah, thank you so much. Thank you so much for joining.
Can you see our screen?
Yeah.
AJ, can you see our screen? We're sharing.
Yes, yes, yes. We can see you. We can see that screen.
Okay, good.
Yeah. So it's my pleasure to introduce Professor T.W. Klein from Cambridge University. Professor Klein is the Emeritus Professor at Department of Material Science and Engineering, Cambridge University, UK. His research interests center on the thermomechanics of composites and coatings, particularly processing, numerical modeling, and fine-scale mechanical interrogation. He has authored more than 300 papers and 2 textbooks on composites and 10 educational software packages. He has been a sole supervisor for more than 80 PhD students in Cambridge University, and he has delivered 50 invited keynote talks. He was the president of Federation of European Material Societies, and he is the director of globally accessed educational material science website also, which is very useful for all students of materials community. He has been awarded the Griffith Medal, a premier prize of the Institute of Materials. He has been elected fellow of the Royal Academy of Engineering as well as Helmholtz International Fellow in 2014. Thank you, Professor Klein, for joining us today. Now, let me introduce Dr. Jimmy Campbell. He is the Chief Engineer at Plastometrics Limited in Cambridge. He completed his PhD degree in Department of Material Science and Metallurgy in Cambridge University. In 2018, he has focused on developing the novel approaches to measuring the mechanical properties of metals via indentation experiments. He has also co-authored about 15 journal papers and textbooks which are focused mainly on testing the plastic deformation of metals. In Plastometrics Limited, Dr. Jimmy has led the design and manufacture of the indentation plastometer, a benchtop indenter with integrated profilometer. The machine, with its automated workflow, creates an indent and scans the residual shape. So he will be presenting with Professor Klein today on obtaining the metal plasticity and failure characteristics via iterative FEM modeling of indentation, the PIP methodology. Professor Klein and Dr. Jimmy, over to you.
Oh, well, thank you, AJ. That's very kind. So, as you say, we're going to try and give some kind of introduction today to a fairly novel methodology, although it's based on well-established principles. And as you also mentioned, we'll do this as a double act. I'll give a talk of about 15 or 20 minutes myself, and then I'll pass over to Jimmy to do the second half. And we'll take questions at the end of both of those, if that's okay, because we're covering essentially the same kind of area. So it is based on work that's been done in the university over the past couple of decades, really. But what's brought it into focus is that there is this startup company called Plastometrics, which is now marketing some products, and you'll hear a bit about the actual machine itself towards the end of the talk, although you can see a picture of it there. So let me just give you an introduction first to what is actually in the talk. So this is the structure. I'm going to start off by just giving some background really to the concept involved. We call it PIP. It's based on making indents, measuring the indent profile, and then doing a repetitive, iterative FEM simulation of the process in order to converge on the best fit set of plasticity parameters. What we're trying to establish is the stress strain curve of the material. And although it does involve a lot of FE simulation, the whole thing takes place rather quickly. So, it's a rather tractable tool if you have an integrated system where you can make the load, create the indent, measure the profile, and then do the software, the iterative FE. So here's the basic idea pictorially. You start by making an indent to a prescribed load using a spherical indenter, a relatively large spherical indenter. You measure the profile rather carefully, and then you need some kind of constitutive law to describe the plasticity. We use the Voce equation. There are alternatives, but you need to be able to simulate the plasticity. So you carry out FEM simulation of the test. You look at the predicted profile, you compare it with the experimental one, and you evaluate the difference between them, the error, this S parameter. And the better the fit, the smaller the value of S. So you decide whether you've converged sufficiently. If not, you repeatedly carry out the FEM simulation with altered values of these plasticity parameters until you you get the best fit, and then that's given you the plasticity law. From that point, you can do all sorts of things, simulating other situations, etc. So here's the kind of thing that goes on during that process. This is actually showing you how that misfit parameter, that S value, is changing with repeated iterations. This is a log scale, so down here we're down to very low values, and we're aiming to get a value somewhere around here, 10 to the minus 4 or so. So these are the corresponding values of the plasticity parameters being iteratively changed until eventually we settle down to something which is the best fit. And all that happens rather quickly during an automated process. So just emphasizing again the sequence, you create the indent using a large spherical indenter. You measure the profile. Here's some different profiles for different applied loads. If you're interested, you can start focusing on looking at the microstructure around the indents. This is showing these persistent slip bands in individual grains, so you can get some feel for what's actually going on inside the material. But the key procedure is then to repeatedly simulate the indentation process, and as I say, get the best fit between the measured and modeled profile, and then that gives you the true stress strain curve. That's what we're trying to obtain. Once you've got that, you can simulate all sorts of things, including the tensile test, for example. So you could put those true stress strain parameters into another model, and you can predict how a tensile test would proceed, including simulation of the necking, etc. Or you could do all sorts of other things if you wanted to. So that's it really, but there's a lot of subtleties in this to get things right. And of course, you do need to understand the difference between true and nominal stress strain fields. So this is the outcome of FE simulation of a tensile test, a particular one. This is the true stress, true strain relationship for plastic deformation. and you can simulate when necking will start. In this particular case, it's here at about 20% strain. Up to that point, the stress and strain fields are uniform. Beyond that, obviously you get a lot of inhomogeneity as the neck starts to develop. And the true strain in the neck is being monitored here, and then it's fracturing at a certain point, which is actually often something you can predict in terms of a critical value of the true strain in the neck being reached, in this case about 80%. So that's the kind of thing you can do. Now the bottom line is what actually happens if you take an unknown material, you make an indent, you carry out this process, and you end up with a nominal stress against nominal strain curve, which you can compare with a conventionally obtained one from a tensile test. So this is just a couple of examples. These are actually both copper samples. One of them as received, as extruded, so quite a high yield stress, not much work hardening. On the other hand, the same material after annealing gets much softer, much lower yield stress, although it then work hardens a lot. And as you can see, you're getting pretty good agreement between the conventionally obtained curves and the ones just from indentation, followed by this iterative FE procedure. So that's the basic idea, and it does work, so to speak. But there are a number of issues, and you need to be confident you're capturing what goes on rather accurately. Another thing you can compare, if you want to, is the way the neck develops. Obviously, you can do this to some extent via the stress strain curve, but also you can look at the shape of the neck. So this is for a couple of different materials. One is copper, another one is aluminium alloy. Different stress strain curves, of course, different true stress, true strain curves. So when you do the simulation, you can compare not only the stress strain curve that you measure, but also the neck shape. And you can monitor how the strains are developing. These are the von Mises strains as a function of position here, obviously reaching a high value at the neck itself. This is just before rupture. And the level of true strain reached in the neck commonly reaches something like 100% or something like that. What else? Well, there's a number of important features of the process if you're going to get this right. And one of them is the scale. And this is an important issue. What scale should you do this on? If you make very small indents, you'll probably be in single grains and you'll get very different behavior. Because if you want to capture the bulk response of the material, you do need to deform a relatively large assembly of grains, what you might call a many grain volume. And the reason for that is that the way the bulk behaves depends on a number of things. It depends on things like grain size, texture, the structure of the grain boundaries, because that affects the ease of rotation and sliding at grain boundaries. And of course, the usual things that you might expect anyway, dislocation density, precipitates, etc., etc. But it is important to deform a many-grained volume. And what that translates into, if you recognize that the grain size could be anything up to 0.5 millimeter or even more, but this would be a typical range up to, say, 500 microns. That means you need an indent diameter, which is at least around 1 millimeter, and probably an indenter radius of around 1 millimeter as well. One of the things this brings in is that you need a reasonably large load, depending on the hardness of the material, of course, but you're probably going to want something in the kilonewton range in order to create this indent. It's still relatively small on a macroscopic scale, but it's not small in the sense of being what you might call nano indentation, which is much, much finer. And nano indenters have load capabilities down in the Newton range, if that. They can't be used for this kind of thing. So you need a special or a suitable loading frame that can generate loads in this range. So that's an important point to note, scale. There's other issues. One of them is what kind of plastic strain do you create during the process? You obviously need to create a relatively large range of plastic strain. If you're trying to capture how the material responds during a typical tensile test or something like that, you need to be going up to tens of percent typically. If you've only created plastic strains of a few percent, you're not going to capture the response over the right sort of range. Now, the plastic strain range depends on a lot of things, but obviously it depends on how deeply you're going relative to the indenture radius. So both of these are going to a depth of, well, a few hundred microns, and they're different materials, so that affects the strain range you get. This is a material not exhibiting much work hardening, so you get quite high strains, quite localized. You also get a big pileup. If you have a material with more work hardening, then the plastic strain gets diffused over a larger region and there's a bit less pile up. But in both cases, you can see that we're generating strains up into at least several tens of percent. And that's the kind of thing you need to do. You need to go down to a reasonable fraction of the indenture radius. Perhaps 20% would be a typical depth to go to generate the right sort of strains. So this all ties in with the numbers I was giving earlier. The indenture radius is about a millimeter. You want to go down to, say, 200 microns depth. And in fact, the way we run this procedure is that we increase the load until the depth reaches a suitable kind of range, something like that, 20% of the indenture radius. So those are important issues. If you want to go deeper into this, you could do something like this. You could say, during the FE simulation, I can note what fraction of the total plastic work is done in different ranges of plastic strain. Obviously, the deeper you go, the more you're going to get work done at slightly higher strains. But you can convert this kind of modeling to this. You can find out the average, the weighted average plastic strain that's been generated as a function of how deep you go. So this again is for 1 millimeter indenture radius. So this is 20% penetration. And as you can see, if you go to that kind of depth, you're generating average plastic strains that are affecting the behavior up around 10 or 15%. And that should be suitable for capturing the behavior overall. Do need to go reasonably deep. So say 20% is a typical value we aim for. Okay, I think at that point, I'll pass over to my colleague, Dr. Campbell, who's going to give you some more information about some of the kind of issues that really turn out to be important in some cases. Things like the material being anisotropic or there being residual stresses, etc. present. So over to you, Jimmy.
Thanks, Bill. So as Bill said, there's two issues we're going to look at. The first one being plastic anisotropy and the second residual stress, which may occur in materials that we're going to conduct our indentation experiments on. So if we look at anisotropy first, one area where we might see significant plastic anisotropy is in additively manufactured metals. This example here is of a nickel-based superalloy, and we can see here on the left-hand side, EBSD scans from two different orientations. So this one in the XY plane, showing a relatively equiaxed grain structure, and this one in the XZ plane, showing that there's clearly been directional growth occurring along the build direction. So it's clear in this case that we've got a strong 100 texture parallel to the build direction, which is what you would expect in nickel-based superalloy. What we can see on the right-hand side here is that this texture leads to quite significant anisotropy between the horizontal and vertical direction. So the horizontal is the in-plane direction and the vertical is the build direction. What we can also see, if we zoom in on the elastic region, is that the material is stiffer in the transverse direction than it is in the build direction, and that is because of the 100 texture. So it is less stiff in the 100 direction. So what happens when we indent this material? Well, on the left-hand side, we can see an SEM micrograph of the indent after indenting in the XY plane. And in this case, the indent is radially symmetric. So in all directions, all of them being transverse directions, we produce the same scan. So there is no difference depending on which orientation we take our profilometry measurements. However, if we indent in the XZ plane, what we can see here is that the indent, when viewed under the SEM, it looks almost elongated in one direction. So in the growth direction, we can see that the indent looks almost wider than in the transverse direction. And that is because of the different pileup we can see on the right-hand side that occurs in the different directions. So in the transverse direction, indicated on the graph as the 0 degree scan, we have less pileup. And in the 90 degree scan, so in the growth direction, we have much more pileup. And what that indicates to us that in the transverse direction, the material is more resistant to plastic deformation, i.e. it is harder, which is the same as that we saw in the nominal stress strain plots previously. So what can we do with this information? Well, if we take the radially symmetric indent, the prediction from pit testing is shown on the plot here. And we can see that fairly good agreement is achieved. We would expect, on the basis that indentation is a multi-axial procedure, so that deformation will occur in all directions effectively, unlike in a uniaxial test where we're only testing in a single direction. And we see that the agreement comes out here closer to the transverse direction, which is what may be expected given that there are more transverse than axial directions when indenting in this plane. At the moment, we have no capability for quantifying anisotropy from an anisotropic indent, but that is an area of active research for us here at Plastometrex. And at least the profiles do allow us to assess that there is anisotropy present, and it reveals some of its nature, i.e. in which direction is it going to be harder or softer. Okay, so if we move on to residual stresses. So the way that we investigated residual stress was using the rig shown on the left-hand side. So it's quite difficult to generate residual stresses of a known or very accurate value. And so how we decided to do it was to apply the load to the sample. So you can see that we've got a cruciform shaped sample, and these 2 points here and here are fixed. And in these ones here, we apply a load through the loading nut and measure effectively the applied load through this strain gauge here. So in 2 different directions, we can pull on these loading nuts, generating a stress in the material, and we hold that constant as we perform the indentation. So previous papers had stated that they used the applied load from this kind of setup divided by the area of the sample in the cross section here to give you the residual stress in the center of the cruciform. Unfortunately, that's not quite right. There are 2 things that you have to consider as well. The first of all are the Poisson effects from the contraction that change that area. That's a relatively small effect compared to the effect of having an effectively large cross-sectional area in these regions just due to the curvature that you have to have on the arms. Now, what that leads to, if we simulate this relatively simple case, is that the stress in the arms here in the X direction and here in the Y direction, if we apply the same load in both directions, we'll see symmetric effects in the X and Y stresses. But you can see that the stress is quite a lot higher in the arm than it is in the center. Now, this leads to the von Mises stress looking not quite as uniform as we might expect initially, but it does result in this central region here having a relatively constant residual stress. So we're looking at the equal biaxial case, and in this region, the von Mises and indeed the X and Y components of that are relatively constant. So we can see here the results of the indentation experiments for different applied residual stresses. So this is in the case of, this is written just as applied loads. And we can see here at the applied indentation load of 1/4 of a kilonewton that there is some differences between the indentation experiments. When we increase that load to a kilonewton and therefore go a lot deeper, we can see that the effect of the residual stress is much weaker. So there is not that much separation between almost all of the cases there. So what we can then do is take those indents. We know the plasticity parameters because we can take that from our indentation experiment performed on a sample with no residual stress. So we know the plasticity properties, we put those into our FE model, and we then vary the residual stress, and we can then calculate the misfit parameter for each of those values of residual stress. And what we can see here is that we do get a minimum and therefore a best fit for each different value. And you can see that each of these does have a minimum rising on either side. And we can see that the correlation at the lower depth is okay. So here the blue one is actually a residual stress of 115 megapascals. That's quite close. There's a bit, it's a bit less well defined in this region, but as we go negative, we have -60 and -30 and -106. But my apologies. -106 would actually, we're predicting residual stress of almost -200 there. And then we can see for the deeper indents, we're getting much less sensitivity to the residual stress. So as we might have expected, looking at those indentation profiles, actually there is very little sensitivity at those depths. And this is summarized in this plot here, which shows the inferred residual stress against the actual residual stress. And we can see that at low penetrations, we're getting a reasonable agreement in terms of at least the correlation, but there's a lot of scatter around that. And then at the higher depth, we're getting very poor sensitivity to the residual stress. So one reason that you can look at to sort of explain this is that after a reasonable penetration, the radial stress fields look quite similar, whether there is no prior residual stress or a tensile residual stress here of 115 megapascals. So you can see that the field is dominated by the plasticity that has occurred. And that may help to explain why we don't see very good sensitivity to the residual stress. So what's the outcome of this if we just ignore residual stress and only try and infer the plasticity parameters? So in our model, we keep the residual stress set to 0, and then we try and infer with different sets of indents where residual stress had been present. So we can see at the low loads, the effect on the yield stress so the yield stress in this case is 200. The effect on the yield stress is reasonable at these lower depths. So we can see it drops down to 100 or up to 250 when we have residual stresses which are 180 megapascals, so quite high in this case. As for the UTS, which should be around 260, we can see that there's a very large spread, and this value can go up quite significantly. So that's all for the shallow set of indents. In the deep indents, the effect is much less, as we might have expected. The effect is much less marked. So the compressive residual stresses will have a very small effect on the yield stress, and indeed the UTS at large penetrations. And the tensile residual stresses we can see have more of an effect on the yield stress, but almost no effect again on the UTS. So again, for relatively deep penetration, we can see that the effect of the residual stress is much less significant than at low penetrations. Okay, so finally, I'd just like to introduce you to the Plastometrex indentation plastometer. You can see here the key components are labeled. So we have an indenter with an LVDT, base plate, and an integrated profilometer. And I'd just very quickly like to show you an introductory video from the plastometer.
Welcome to Plastometrex. This is one of our indentation plastometers. Today, I'm going to show you just how simple the workflow is. Here, we have some aluminium plate, and for sample preparation, we've done a quick surface grind, and we've ensured that we've got a flat surface for indentation. To run a test, place the sample underneath the indenter head. Once you click start, the indenter head will come down, and the LVDT will come into contact with the sample surface, and the indenter head will pause. This allows you to make any fine adjustment to the position of your sample for the test. Once that's complete, everything from this point on is automated. The indenter comes down and touches on the sample surface and then begins to indent. If we look in our Corsica software, we can see the load displacement plotted as it is being acquired. Once the indenter has reached the appropriate load, it then unloads. The profilometer now comes across. The sequence the profilometer follows will be that it touches down on the sample surface. It then moves to within the indent and finds the center of the indent. It then moves back outside the indent and performs a scan straight through the center of the indent. Now we move into SEMPID, which will convert our residual indent profile into stress strain data. The straight into the software, and the user must then specify the material. This is important as it defines the stiffness which will be used in the calculation. Here we've indented aluminium, so I will select that as my material and perform the analysis. This will typically take around 10 seconds. Now that the calculation is completed, we can see here we are using the Voce plasticity equation, and underneath are the parameters that SEMPID has calculated in that equation for our stress strain data. On the plot, the dotted line shows this plotted as a true stress, true strain relationship, and the solid line shows that true stress, true strain relationship converted to a tensile nominal stress strain. This also allows the calculation of the UTS, or ultimate tensile strength, which here occurs at approximately 10%.
Okay, so it's just a short introduction video showing you a bit about the workflow. So in summary, we've looked at inverse FE modeling to infer the stress strain properties of metals. It's a transparent process. However, for it to be reliable and accurate, we've got to satisfy several conditions. First, as Bill outlined, is the scale. To ensure that the bulk characteristics are captured rather than just those in a single grain where the properties are highly anisotropic, and we don't actually capture all of the properties such as the influence of grain boundaries. We must ensure that the diameter is large enough, typically of the order of a few millimeters, to make sure all of the microstructural features are captured. Spherical indenters are typically the best ones because they don't have any issues such as sharp corners. So the modeling, there's no problems with the modeling. And the residual indent profile is a much more sensitive outcome to the properties than the typically used load displacement plot. To characterize plasticity over a useful range, we've got to probe relatively deeply, around 20% of the radius, which means if you're going to use a millimeter-sized sphere, you need loads in the kilonewton range. So we then had a look at anisotropy, noting that indentation is multi-directional, so we get a direction averaged response. And we looked at the case of a nickel-based superalloy. Residual stress can affect the progress, but the sensitivity is low. This is especially true for larger penetrations, although it can have some effect at lower penetrations. And finally, we just had a quick look at the Plastometrex indentation plastometer, which will automate all of this for you and predict stress strain properties from indentation within 2.5 minutes. So I'd like to thank you all for tuning in today, and we'll be happy to take some questions.
Thank you so much, Professor Klein and Dr. Jimmy. Now, I request all the participants to, if they have any questions, they can ask. We have Professor Nikhil Gupta and Professor Mohanty also there. If they have any specific questions, they can also discuss.
Hello.
Yeah.
Yeah. So somewhere in the slide you have shown that using EBSD measurement, you have shown the two cross sections, basically two planes of the additively manufactured nickel-based superalloy, and then we are calling it as some kind of texture is present 101, I guess. Yeah. Here only. And then when we are seeing the residual indents, and that time we are comparing the shape of those indents. So that shape is coming because of some crystallographic texture, or is it just the grain morphology which is resulting in this type of shape change?
I think you're asking whether it's the shape anisotropy of the grains or the texture that's causing the effect. Is that what you mean?
Yeah, crystallographic texture. Yes, sir.
Yeah,
Yes.
well, I think, I mean, we're just seeing the outcome, but I would expect it would be the texture that would have the strongest effect. I mean, the shape of the grains is relevant, but it's probably more dependent on exactly
because on one plane we are seeing very elongated grains, and on the other side we are seeing more of equiaxed grains. So is it just the effect of grain shape, or some
well, as I say, I mean,
texture?
both could be contributing, but I think it's the texture probably that's the most important. You see, what's happening here is that obviously assemblies of grains are deforming in a cooperative way. If there is no texture and the grains are equiaxed, then obviously you'd expect it to be isotropic, to deform in a similar way, no matter which direction you loaded it in. But if it is textured, and if it has shape anisotropy, there will be some differences. And here you're clearly seeing that it's harder in transverse directions. So
yes.
I think the answer to your question is I suspect it's the texture that's the more important of the two.
Actually, we have seen some papers in the Journal of Additive Manufacturing on SS316, basically the steel, and there they have shown that because of the shorter slip path, this anisotropy comes in the bulk samples, like we are seeing here also. And I suspect that it may be because of grain shape also, like in the TI-64 and SS316 people have reported.
Yeah, I mean, you're absolutely right. And unless you do some very detailed modeling, it's quite difficult to separate the two. Certainly the texture is quite strong. You can see that here just from these EBSD. I think there's a factor of about 4 from randomness in terms of the bias of 100 directions being aligned along the growth direction. So it's quite a strong texture, quite a simple one actually, but it's not simple to predict how that will plastically deform. You would need to do
some kind of crystal plasticity simulations, maybe.
Yes, it can be done, I'm sure. But all we're seeing is the net outcome here. And you're quite right, it could be getting influenced by both shape, anisotropy, and texture.
Yeah. Thank you, sir. And when we are simulating this tensile test using the Bose parameters obtained using the iterative FEM simulations, then how are we considering the effect of voids in predicting the necking?
The effect of voids, you said, did you?
Yeah.
Jimmy, do you want to take that?
Yeah. So we're not considering the effect of voids in the onset of necking. So if we look at this plot here, you can see that the nominal stress builds up to the maximum at around sort of just under 1100, and then the neck just begins to form, and that is just a geometrical effect, and indeed was predicted by Considere a long time ago. So in terms of the beginning of the formation of the neck, that is, as I say, it's a geometrical thing. You can predict it both from FE or just from converting the Voce equation in its true form into the nominal form. And again, you'll predict a maximum. And it's then just the instability that will lead to the neck forming. In terms of, if your question is related towards porosity and voids in additively manufactured materials, certainly they can act to promote fracture prematurely. So maybe earlier in the necking, once the material has necked, or maybe even before necking. And that is something that we can't capture with indentation. The stresses in general are compressive, and therefore we're not stimulating any fracture during the indent. But there is no consideration of voids in the simulation, because actually you predict the neck without any voids. That's just a continuum.
Okay. Thank you, sir. Thank you very much.
Yeah. Thank you, Rupam. Any other questions from the audience? So Dr. Jimmy, you have shown one video that so I wanted to know what should be the sample roughness do you expect?
So what sort of roughness is acceptable? Is that the question?
Sorry, are you asking what kind of surface preparation is needed?
Yeah.
I mean, the answer to that is that it doesn't need to be highly polished or anything. I mean, one of the big advantages of doing this on a relatively coarse scale is that it's not very sensitive to surface roughness. Of course, if it's very rough, if you have a thick oxide layer on the surface, or you have very, very deep grooves or something, then it might create an error. But generally speaking, you just need to grind this to a reasonable finish. You don't even need to polish it. And if you do polish it, you certainly don't need to polish it very finely.
Yeah, so we typically recommend that a grind of P1200 grit is appropriate. That's more than enough. So we don't suffer, like Bill said, the problems that you might associate with nano indentation, where you do need a very good finish to make sure that that's not going to affect the response of the material, because you're indenting on such a fine scale. So the requirements for surface finish are actually not too demanding.
Okay.
I mean, there is one point you might like to note there, which is that if you do get a reasonable finish, you might see some interesting things. like here, for example. Now that's just the free surface there around the indent, and it was well polished beforehand. And you start to see some interesting things like these persistent slip bands where lots of dislocations have followed each other and reached the free surface. In fact, if you look carefully, you can see other things. You can see deformation twins or prior annealing twins. And you also see grain rotations.
Right.
So this kind of thing becomes clearer if you have created a polished surface to start with. But in terms of actually doing the test, you don't need a polished surface.
Right. Okay. Okay. Can you go to your residual stress slide? Just I wanted to say one detail. So there, here, what you are doing is you are stretching the samples from both sides, right?
Yeah.
And then you are doing the in situ indentation.
Yeah.
Okay. Okay. Thank you. Yeah. So any other questions from audience before? Yeah. So if there is no more questions from the audience, let us thank Professor Klein and Dr. Jimmy for the very valuable talk, and they have shared that very innovative technique for measuring the mechanical properties of the material. Thank you so much. Thank you so much, Professor Klein and Dr. Jimmy. Thank you so much.
Thank you, Ed.
Yeah. Now, we will move to the next talk by Professor Surya Kalgundi. Professor Surya, are you there? Professor Surya? Professor Surya, are you there? I think he will be joining soon. We will wait for a moment. I think we are half an hour ahead. He will be joining maybe in 15 minutes, so we will wait for once he joins. I request all the participants to stay connected. Professor Surya will be joining shortly. So Professor Surya will be joining in another 15 minutes. By the time we will be showing our institute and department video for you to have information about our institute and department. Thank you.
Department of Mechanical Engineering, IIT Tirupati welcomes you. The Department of Mechanical Engineering at IIT Tirupati was established in July 2015. At present, the department comprises 13 full-time faculty members and 12 staff members across the specializations, solid mechanics, fluid and thermal sciences, and advanced manufacturing. The department houses well-equipped laboratories which are used for both instruction and research. Our major thrust areas in research include advanced manufacturing, advanced materials, renewable energy, theoretical and applied mechanics, and precision agriculture and food processing. Advanced manufacturing is one of the thrust areas of IIT Tirupati. The research activities under advanced manufacturing are broadly classified into advanced welding and additive manufacturing, advanced machining and micro nano finishing, advanced casting, and advanced metrology. With the state-of-the-art research facilities, the Advanced Welding Lab in the Department of Mechanical Engineering is actively working on various cutting-edge welding technologies to cater the needs of heavy fabrication and automobile industries. The research work funded by Defense Research and Development Organization, DRDO, on the tandem submerged arc welding process mainly focuses on developing the welding technologies to improve the productivity and quality of the welded joints associated with the ship and submarine building. Narrow gap joining has been adopting fast for joining thick plates. However, the lack of understanding on the complex arc physics within the narrow groove leads to the difficulty in getting the sound welded joints. The research work funded by Naval Research Board, NRB, focuses on understanding the arc physics involved in the narrow gap joining of the thick plates using tandem gas metal arc welding process for heavy fabrication applications. The thrust for increasing fuel efficiency forces the automobile industry to reduce overall weight of the vehicle. This motivation attracts the automobile industry to replace the steel with high-strength aluminum alloys. However, joining aluminum to steel is a challenging task due to the vast difference in the thermophysical properties. Research funded by Science and Engineering Research Board, SERB, focuses on developing the technology for the aluminum to steel dissimilar joining using cold and hot wire gas tungsten arc welding process. Friction stir welding of one of the shape memory alloys is also one of the active research happening in the Advanced Welding Lab. A significant research work on the numerical modeling of the welding process is going on to understand the temperature distribution and its influence on the welding distortions and residual stresses. The additive manufacturing facilities, like the state-of-the-art wire arc additive manufacturing (WAM) process, fusion deposition modeling, and powder bed fusion process yet to be installed, helps in the cutting-edge research activities to support the research in aerospace, medical, and marine industries. The research in the area of numerical modeling of wire arc additive manufacturing and powder bed fusion process helps in defining the optimum process parameters even before performing the experiments to manufacture the three-dimensional components economically and with minimum defects. Micro nano finishing is the another area where diversified research work is going on. The patented abrasive flow finishing technology using fluid-based advanced cutting tools efficiently produce the nano finished surfaces. The expertise is also available in the laser microtexturing to develop super hydrophilic surfaces, developing the bioceramic functionally graded coatings for orthopedic applications, manufacturing biocomposite based internal fixation devices, micromachining using bioorganisms, biomicromachining for microfluidic biomedical devices, and polishing the advanced ceramics such as silicon carbide by controlled laser beams. As a part of advanced casting research, Foundry 4.0, Student Activities Center F4SEC is established in collaboration with Indian Institute of Foundrymen, IIF. Foundry 4.0 is a smart manufacturing with greater computing power, connectivity, feedback, and digitization of the physical world. Foundry 4.0 encompasses the technologies that make shape information move faster, more accurately, and with reduced physical effort as it is transformed into useful physical objects. In order for the metal casting industry to attract the younger generation and to be competitive, there's going to be a need to absorb some of the advanced manufacturing options available today that are being utilized in other industries. F4SEC has following advanced casting facilities: stir casting, squeeze casting, pressure infiltration, vacuum casting, vacuum arc melting, induction melting, and casting simulation. Engineering components need to be accessed for their GD and T callouts apart from the dimensional tolerances. Under the advanced metrology domain, we have the expertise to develop certain algorithms for the evaluation of their form errors such as straightness, flatness, circularity, cylindricity, etc. The software developed based on these algorithms can be developed in the advanced metrology instruments such as CMMs and other form testers. We have fully developed metrology lab with sophisticated equipments like CMM, autocollimator, 3D scanner, form tester, and contour and roughness testers. The research activities under fluid and thermal are broadly classified into energy and hydrogen storage, spray and combustion, fluid energy and renewable technologies, and fluid machining and modeling. First project, metal hydride absorb and desorb hydrogen reversibly for few thousand cycles. Hydrogen absorption is an exothermic reaction and desorption is an endothermic reaction. As cyclic absorption and desorption of hydrogen by metal hydrides involve heat interactions, they are found suitable in many energy conversion cycles like thermal compression of hydrogen, hydrogen purification, thermochemical energy storage, etc. One of the important aspects while using these metal hydrides for these applications is their ability to resist impure gases in the hydrogen and stability during prolonged cycling. In this project, we are studying the effect of impure gases such as carbon dioxide, carbon monoxide, oxygen on hydrogen storage characteristics of AB5 type metal hydrides. We are also studying the stability of these hydrides after prolonged few thousand hydrogen absorption and desorption cycle. All these tests are conducted on a fully automatic PCT Pro instrument. Second project. So far, the thermal energy storage systems developed using metal hydrides work at low or medium temperature up to 400 degrees Celsius. New materials are needed to be investigated for storing thermal energies above 600 degrees Celsius. We have developed an experimental setup for testing the performance of thermal energy storage system at high temperatures. Third project. The goal of this project is to develop high-efficient thermal-based multi-stage hydrogen compressor, which will be cost and performance superior as compared to the other alternative systems for hydrogen refueling stations. The performance of hydrogen compressor will be tested at different operating conditions. In particular, the overall system efficiency, stability upon recycling and hydrogen delivery rates of a hydrogen compressor will be studied. Detailed cyclic stability tests will be carried out. Economic analysis on the developed prototype of the hydrogen compressor system will be done. Fourth project. The project is focused on selection, synthesis, and characterization of thermochemical materials for thermal energy storage. The performance of the proposed thermochemical energy storage system is evaluated at different operating conditions. Spray and Combustion Research Group at IIT Tirupati is working on industrial relevant projects. The research on micro-explosion fuel blends will help in using alternative fuels such as ethanol and biodiesel effectively, thereby reducing emissions. The research work on atomization of high viscosity fluids is targeted at using liquids with high dry matter content, thereby reducing energy consumption in spray drying process. The group is also working on development of energy efficient twin fluid atomizer development for carbon dioxide capture from the flue gas along with BRNO University of Technology, Czech Republic. The Fluid Energy and Renewable Technology Lab is interested in the design and development of a fixed wing drone for characterizing the flow behind a full-scale wind turbine. The drone is instrumented with a 5-hole probe for the real-time measurement of the wind velocity vector along its trajectory. An autopilot system on board provides the drone with fully autonomous flight capabilities. These electrically propelled drones, such as pusher prop configurations, are designed for best-in-class endurance. It is a self-funded project. It is no secret that a good wind tunnel facility plays a crucial role in the development of such drone platforms. Thus, we are also presently focused on 2 other important projects, namely, design and development of a low turbulence wind tunnel test facility at IIT Tirupati, and the development of a first of its kind 6-component balance. The open circuit wind tunnel facility will be one of its kind in India, with test section turbulence levels at least 1 order of magnitude smaller than those present in any comparable test facilities. Also, the goal is to achieve it with at least 25% reduction in power consumption through active flow control. The other projects involving balance will enable dynamic measurement of net forces and moments acting on a drone or a scale model of a wind turbine that is being tested in a wind tunnel. The balance will boast a resolution of the order of 0.005 Newton in forces and 0.05 Newton meter in moments. Both wind tunnel and balance designs will be scalable, and IIT Tirupati funds these 2 projects. The results from this research shall be useful in the energy and defense sectors. The Fluid Flow Modeling Research Group at IIT Tirupati is interested in investigating flow phenomena using a combination of mathematical modeling, numerical simulations, and occasional experiments. Of specific interest is the study of propagation and evolution of waves at the interface of 2 fluids with applications to ocean swell. The goal is to produce accurate models for swell dissipation, which affects air-sea interface interactions, upper ocean mixing, coastal dynamics, sediment transport, and wave climate. Efforts are also underway to experimentally investigate the rheological behavior of complex fluids with long-term aim of investigating sea surface microlayers that compress complex fluids, biofilms, phytoplankton, zooplankton, and their byproducts, polysaccharides, polymer and gel particles, aggregates, crud dust, and oil resulting from spills. The result of this research shall be useful to people working on weather forecasting and climate modeling, earth system modeling, coastal engineering, and oceanographic studies. The research activities under solid mechanics are broadly classified into automotive dynamics and vibrations, theoretical and computational solid mechanics, biomechanics, and composites. Physics-based digital twin for automotive brakes is a project funded by SERB, aims at developing an intelligent system which helps us understand the true condition of an automotive brake and tells us when and why it will fail. This is executed using mathematical modeling, experiments, and machine learning techniques. Gears, clutches, brakes fall under the category of combined rolling sliding contact systems. The research going on focuses on the concept level understanding of the dynamic behavior of the systems. Effort to understand the human movements mathematically. What drives a particular style of motion for a given person? The research group in a theoretical and computation mechanics focuses on phase transformation and plasticity and their interactions. Presently, the research work is going on the interface-induced solid melt phase transformations and Merton-Scientific phase transformations in polycrystalline solids. The research work also includes the interactions between plasticity and Merton-Scientific phase transformations in crystalline solids. Auxantic materials are a class of architectured materials that exhibit negative Poisson's ratio, meaning they expand and shrink laterally under tensile and compressive loading, respectively. The study focuses on the energy absorption characteristics of sandwich structures with chiral exotic cores under dynamic impacts and blast loading for design of protective structures. The study shape optimized structures focuses on in-plane behavior of 3D tempered I-beams with simultaneously tempering web and flanges, and with monosymmetric and bisymmetric cross-section that have wide applications in aerospace, shipbuilding, and construction industry. The novelty of the approach is that it lends itself to a simple closed-form solution which can be used as a design tool for practicing engineers. IIT Tirupati, thanks you for your time. Department of Mechanical Engineering, IIT Tirupati.
Yeah, so dear participants, just now I spoke to Professor Surya. So he is just joining in 5 minutes. Okay. Yeah. So actually there is a time difference. There is an early morning there. So he is joining in another 5 minutes. Hello.
Hi.
Professor
Hello.
Surya. Hello.
Hi, I can hear you.
Yeah, hello. Good morning.
Good morning.
Yeah.
Good evening for you.
Yeah, I think we are half an hour ahead, so small delay. So shall we start?
Yes.
Yeah.
Please.
Okay. Thank you so much. Thank you so much. So, dear participants, again, good evening to all of you. So we have Professor Surya Kalidindi from Georgia Institute of Technology, USA. So it's my pleasure to introduce Professor Surya. He is a Regents Professor and Rai S. and Frank H. Neely Chair Professor in the Woodruff School of Mechanical Engineering at Georgia Institute of Technology, Georgia, with a joint appointments in the School of Material Science and Engineering, as well as the School of Computational Science and Engineering. His research efforts have made seminal contributions to the fields of crystal plasticity, microstructure design, and materials informatics. He has been elected a fellow of ASM International, TMS, and ASME. He has also been awarded the Alexander von Humboldt Research Award, the Vannevar Bush Faculty Fellow, the Government of India Vajra Faculty Award, and the Khan International Award. So with this, I would like to request Professor Surya to deliver the lecture. Professor Surya, over to you.
Thank you. Let me share my screen first, and let's make sure that, that this works. So is everyone, are you able to see my screen?
Yeah, we can see your screen.
Okay. Well, let me start by first thanking the organizers for giving me this opportunity. Yes, there was some sort of a miscommunication in time. I thought I was starting half an hour after later. It turns out that there was just a miscommunication somehow. So anyway, so this is where we are. Sorry for the delay. So I'm going to talk to you about my work, my group's work, my research group's work. This is focused on AI-based materials knowledge systems for they're targeted mainly for accelerated materials innovation. So for those who are not familiar with this problem, the general experience in materials development is it takes about 15 to 25 years from the discovery of a material in the lab to actual commercial products. And that long cycle, 15 to 25 years, is too long. So our effort or our research effort is primarily targeted at speeding those cycles or accelerating those cycles. So why can't we do it in 3 years? Why can't we do it in 5 years? When you can design an entire new jet engine in 1 year and build it, why does it take so long to develop and deploy new materials? So that's the main target in this research. My research is funded by various federal agencies here, Department of Defense, NIST, NSF, as well as the VBFF, Vannevar Bush Faculty Fellow. So with that, let me give you a little bit more detail of a little bit higher level view of the vision of what we want to do. So this is basically a lot of, you must have seen this before. This is how people think of materials. Materials have a hierarchy of length scales all the way from atomic scale to all the way from the atomic scale to the mesoscale. There are many length scales over which materials, there are details of materials that control the properties and performance of the final product. So the final product here is something a designer or a manufacturer is interested in. And essentially, most of this happens in material science, right? Most of this side of the line. So the question, and often when design and manufacturing people on this side have some questions in terms of, how can we improve the yield strength of the material? How can we improve fracture strength of the material? Or, anything like that, any improvement on the material side that's necessary. Of course, they also play a lot with the geometry, but leaving the geometry aside, if you really want to keep the same geometry but increase the material performance or properties, then you have to leverage the understanding or knowledge of all the of what we know about how chemistry affects properties, how material structure, defects at the atomic scale, defects at areal defects, volume defects, and point defects, how those affect properties, and even just grain shape and size, for example, or porosity, mesoscale porosity. So there are a whole lot of things that happen in the material, at the material scale, that need to be optimized in some sense if we want to get a different set of properties, a different combination of properties. So this currently happens in material science, but it happens when one material at a time or one property at a time. So it's very, very slow. So when there's a question here, usually it takes many experiments and many simulations on this side to combined to be able to deliver back the increase that people are looking for, or the increase or change in a particular combination of property they're looking for. And so that's what is very slow. So our concept is that we should be able to build these knowledge systems, what we are showing you here as with this disks, computer memory disks, I guess, are knowledge systems that you should be able to capture these relationships, all of these relationships, this huge library of relationships in these PSP linkages or process structure property linkages defined at different length scales. And one should be able to organize this into a knowledge system that talks to each other. So the knowledge systems talk to each other, and they're able to communicate both in going down in length scales as well as going up in length scales. So classically, going up in length scales is called homogenization. Going down in length scales is called localization. And so in principle, one should be able to build these knowledge systems in such a way that at any instant in time, if there's a question from the design and manufacturing side, we provide an answer instantly, immediately. Now, not saying that, oh, I need to do a few more experiments, few more simulations. I can get back to you in 6 months or whatever it is. Right now, typically, most projects design, if somebody asks a question, it takes a minimum of 3 months for each question. And by the time you actually get it into a product, that's where it takes years, several years. So the idea is that we should be able to collect, aggregate, curate knowledge, not just data, but knowledge, right? I mean, a lot of people are talking about data, but data by itself is disparate, meaning that data you get from different experiments and data you get from different simulations is not exactly consistent, right? So it is not in the same format. It doesn't present the same insight. So how do you take that disparate data and convert it into these knowledge systems? So these knowledge systems should be like, they should be able to answer a question, pretty much almost like your Google-like interface. If you imagine a Google-like interface where people here in design and manufacturing are asking a question, and we provide instant answers, give them different choices. And actually, on top of everything I said, we also need to be able to quantify the uncertainty. So when we give an answer, we need to be able to say, oh, I'm very confident about this answer. I'm 90% sure, or no, there's not enough data, there's not enough knowledge. I'm only 10% sure, but I think this is the answer, right? So we need to be able to give uncertainty quantify. We need to be able to quantify uncertainty in our answers. Once we give answers and quantify uncertainty, people in material, in design and manufacturing actually know how to take advantage of that answers. They know what to do. You don't have to worry about that. Okay, so that's our vision, and that's our where we want to drive this. And what we are doing is to build all the foundational elements needed to build this knowledge systems. These systems don't exist right now anywhere, and we are trying to systematically build all the systems that are necessary. So just to give you a little bit more detail of what we envision. So we envision these PSP models. So we envision data that's related to process, but in each table here, I'm giving examples of variables that would fall into process variables or structure variables and property variables. And in general, as you go down the table, you see details at the atomic scale. So at the top of the table are details at the mesoscale. Bottom of the table are details at the atomic scale. And these lists are not comprehensive. There are many more variables. That's why it's complicated. If it was a limited number of variables by now, we would have done it, right? Humanity would have done it. Because these details are very complicated and there are very large number, assembling this is not that trivial. So going a little bit more detail, both process and properties have at least well-defined mathematical terms, in the sense that we know exactly what we mean when we say conductivity or permeability or something like that. And likewise in process, we know exactly what we mean when we say chemical composition or placement of spatial locations of atomic scale defects and things like that. The main issue really is that structure has no mathematical definition. It's still very qualitative. So when somebody says microstructure, it's not very clear what exactly do they mean. Is it mathematically defined? Some are better defined, some are less defined, but essentially, even when there's a definition, the amount of information that is contained in the structure is very large. It's a very high dimensional representation. So because this is a very high dimensional representation, it's not very easy to connect process, limited a smaller number of variables to this very high dimensional information, again back to a smaller set of variables. So obviously, only way to do this is to get suitable low dimensional representations of structure, so that you can bring this to the same level playing field as process and properties. If we can do that, then there's an opportunity to do what I just showed you in the previous slide. So as you might imagine, this is mathematically fairly intense, a lot of details involved. I'm not going to go into too many details. I think I only have a couple of slides of math, so that's all I'm going to do. But more details are available. In most of my slides, there is a reference here to where you can find more details. So feel free to look at it. So the framework we use is a Bayesian framework for building these linkages. And in particular, the way we use the Bayesian framework is we center it around governing physics. So just as an example is that just from at a high level logic, to build these PSP linkages in these spaces is very complicated, because the spaces are very large. The space of all materials is a gigantic space. So the only way you can do that is you're hoping to get some with limited data. If you rely only on interpolation, you will only be able to explore limited spaces. So you're hoping to get some extrapolative capabilities. If you cannot get extrapolative capabilities, then this entire thing is not going to work at all. So to get extrapolative capabilities, if you just use simple machine learning tools, there's no reason to get extrapolative capabilities. So you have to actually formulate this in such a way that you're getting the extrapolation has to come from physics. So the way we are formulating this machine learning framework is to say that all data that's available, whether it's experiments or simulations, is aimed at updating the physics. And once we have a better idea of the physics, then we actually make predictions, right? So in these kind of equations, phi is the governing physics. So if you give me a piece of material and say, what's the governing physics in that sample? In a Bayesian update, what we say is there's a prior. So this is a prior. So this is what we think it should be, or what people in general think it is. So there's a lot of uncertainty usually in the prior. So you have some rough ideas, but you don't know for sure. Then you're saying, what are the available observations? So there are a bunch of observations, and this term is called likelihood. In Bayesian update, you have a prior, you have a likelihood, you have a posterior. So this is called posterior. The likelihood is simply computing the probability that you're able to actually make that observation. So if you made these observations, what is the probability of, just like the word likelihood says, what is the likelihood that you could have made that observation for a given physics? So this is likelihood is always computed for a given physics, along with the uncertainty in the observations or variance in the observations. Okay. So if you have the prior and you have the likelihood, Bayes' theorem says you should be able to compute a posterior. There's a lot of mathematical techniques on how to compute the posterior, but you can actually get a posterior. And this is now your updated physics given the experimental observations, right? So you had a prior guess, an initial guess, you made some observations. Now you're saying, now I want to improve my prior. I want to improve my guess. And so if you do this in this way, it's very systematic, and it leads to a very systematic way of learning the physics. So if it is that simple, why haven't people done it so far? The complication is that computing this likelihood, because its likelihood is for a given physics, right? So you're saying, and you should be computing it for all kinds of, especially if you're uncertain about physics, you should be computing the likelihood for every instantiation of your physics, every likely instantiation of your physics. So that's a lot of work, especially in materials where you have multi-scale physics and multi-physics at each scale. Computing this likelihood is not trivial, right? And that's where we are going to spend. I'm going to walk you through quite a few examples where I'm going to show you how to compute this in an efficient way. And most of it has to do with machine learning algorithms. And we are using mostly Gaussian process models, or Gaussian process regression models. But we have also used CNNs and neural networks and all those things. But essentially, that's where we're going to get good at. And to do that, we are going to build this. We are going to build these reduced order models, either in the form of a process structure model. So this is a process structure model. Given a process variable, given a physics, what is the structure? Or we are going to build it in a structure property model. So given a structure and given the governing physics, what is the prediction? How do you predict the property? So we're going to build reduced order models, a very large library of reduced order models, and cast them in this form, in this particular form. One is the process structure form, the other is the structure property form. Given these reduced order models, because the models are fast to evaluate, they're significant, they're calibrated to physics-based models. So they're calibrated to models like density functional theory calculations. They're calibrated to dislocation dynamics, phase field models, finite element models. So they're calibrated to physics-based simulations. But we don't, once we do the surrogate models, we don't run the physics-based models anymore, because we can pretty much replicate their capability into these models. And we use this cheap surrogate models to compute the likelihood function, right? So that's step one. And step two is that once we're able to do this and we are able to run this, we can actually now even get greedier, and we can get even more better. And we can now say, oh, I'm not just happy with updating my physics. Now I actually want to design the experiments in such a way that I maximize the gain, right? There is a prior, there is a posterior. That means there is a gain, there's an information gain in each. Every time I do something, I have an information gain. Whether I do an experiment or a simulation, I have an information gain. So, but this time I want to do the experiments, or in fact, run the simulations. Either way, I want to do only those activities that actually maximize the information gain. So that's called sequential design of experiments. So in this one, it says physical experiments, but it could be simulation, numerical experiments, or physical experiments. It doesn't matter. But you can do this sequential design. So you're asking, what is the next best thing I can do? And that there are again tools to do. Once you accept this framework, the Bayesian framework, there are tools that can help you, give you very specific recommendations or answers on which ones to do. So we want to build this, and we want to build this at such a scale that this is fully automated or even autonomous, right? Autonomous is that we can teach a computer to decide all this automatically. So if we can teach a computer to autonomously decide what the next experiment or simulation should be, then we can actually think of autonomous research laboratories or autonomous explorations, autonomous research, right? So that's basically where we are pushing forward. So with this formulation, you can build what we are calling as knowledge systems that can do a lot of functions like diagnose, predict, recommend. I'll try to show some examples as we go along, but that's basically where we are. Now, one more detail before I show you examples. Most of the rest of the talk is examples. This has to do with how do you quantify the structure. So here we use what are called as endpoint spatial correlations. This has been around since 1950s and 60s. Not very much used a little in material science, not very much used in material science, but initially started in chemical engineering with atomic structures, and then got into microscale to some extent, microstructure to a small extent. I think now it's becoming more popular. People are beginning to recognize the benefit of these formalisms. Basically, anytime you look at structure, and in this case, you can see this is a patch of imagine that this is a patch of a microstructure, but it could also be atoms, right? You can, anytime you describe structure, material structure, all the way from atomic scale to the mesoscale, you have a structure that you're trying, a pattern, a spatial pattern you're trying to define. And the best mathematical way of defining a pattern is endpoint statistics. And what I'm showing you here on the right-hand side is what is called as a two-point statistics map. The equation for two-point statistics is here. So M is actually the initial structure. So you can imagine that you can think of this as zeros and ones if you like. So M is an array or a vector. You can flatten this out and think of it as a vector. And essentially what it is saying is the autocorrelation is, the interpretation of autocorrelation is the probability of finding a local state N and a local state P at the tail and the head of a vector R. So R is a vector. So any one of these, for example, these are all R, a given R. So any one of these vectors, if you throw randomly into the microstructure, you're asking what is the probability that the tail is N and head is P. N and P could be any states. For example, in this structure, the states are only two, black and white. So N and P can take only two values. N can be white and black, white or black, and P can be white or black. So there are 4 combinations here, but the number of vectors is very large. I'm only showing you one vector. So if you compute that value, this value is a scalar value. It's actually probability because it's the number of successes that meet that criteria by the number of atoms. So, so that number is this, and so this is, let's say, 15% or 20%, whatever this number is, 15%. So it says that there's a 15% chance of this vector randomly placed. There's a 15% chance that the tail is in white and the head is also in white. So for example, the red vectors are successes, the yellows are failures, And there are different ways you can think of the purple ones. So if the purple ones, if you allow for periodicity, you have purple ones that are also valid trials. If you do not allow for periodicity, they are invalid trials. So nevertheless, there is an entire formalism for this that's worked out. So the argument is that the map here that is showing these colors from blue to red is actually a statistical quantification of this micrograph of this pattern. So it has a lot of information, and this is of course 2-point statistics, and then you can go to 3, 4, and so on and so forth. It goes up and up. So basically, what we have done in the last 10 to 15 years, maybe, is we have produced codes that can very efficiently compute this, mostly using fast Fourier transforms. So we have devised solution methodologies or computational methodologies that will compute this really fast for very complicated microstructures. So these are only black and white, but we do for polycrystals, we do it for atomic states, we do it for dislocation structures, dislocation networks, all kinds of stuff, but using the same general idea. Now, the second problem is that after you do this, you're not done, because now you're converted from the structure to a statistical map. But even this map has way too much information, because the number of states, the combination of states explodes, and the number of vectors is also very large. But this is a very large vector of features. So to reduce the dimensionality of the vector of features, so this is the same vector of features, we put it into a PCA, or we do a PCA, principal component analysis, which is nothing but you mean subtract, center it, or mean center the data. So imagine putting this FR on this side. So you mean center the data, and then you put it into an orthogonal representation. So this is a Fourier basis. Phi KR is a Fourier basis, orthonormal basis. And these are the coefficients. And these coefficients are called PC scores. So that's what we do. So we take every microstructure gives you one vector, one very large vector in millions. So the dimensionality of this typically, by the time we compute them for a real microstructure, is in millions. And we reduce them to a few dimensions. So in this particular case, we are showing that 3 of those dimensions, 3 PC scores, the first 3 PC scores are enough to capture this million-dimensional vector to a reasonable accuracy. So obviously, what is captured using only the first 3 is this. The real 2-point correlation is this one, but we are only capturing this. But at 3, we are still capturing over 90-95% of the detail. And so that's where the dimensionality reduction comes in. So in our representation, microstructure is always represented by a finite number, a handful of PC scores. We have not used more than 15, 20 PC scores in some of the complicated problems I'm going to show you. In the simpler problems, it's often just 2 or 3. Okay, and they're amazingly they're remarkable in how they capture the details of something that's so complicated. So, but that's the trick. That's what we do. So from now onwards, these are mostly examples. I hope I gave you some idea of where they come from. I'm not going to talk anymore about the theory. And this is mostly examples. And then I will talk about the experimental side. Remember I said we have to learn how to get the surrogate models for the physics fast. So that's step 1. Step 2 is how to do experiments and high throughput experiments, and also do the smart experiments, the experiments that actually produce better, more information, high information experiments. Okay, so step 1, how do you compute, or how do you use what I showed you to build very efficient, computationally low cost models. So here we built a model for plasticity, stress strain curves. So into our system, you can put in, as a user, you can come in and put in any 3D microstructure. You can choose anything you want, any volume fraction, any shape, anything you want. Not only that, you can assign any hardening law to to the each phase. So the blue phase and the red phase, you can provide any hardening law you like. Instantly, within a few seconds, the system will predict a stress strain response. So the blue line is a mean response, and it says the red is uncertainty. So it's actually not only predicting the actual stress, what it thinks is a stress strain response, but it is also saying what is the uncertainty in the prediction. And then the black dots are if you actually run a finite element simulation, given the same information, give it to a finite element code, this is what you get. But we are obviously hundreds of times faster than a finite element code because, as you know, finite element codes are slow, especially when the structures are big, microstructures are big. So we can do this for any hardening laws of system, of individual phases and any microstructure. And it's very fast. So that you don't think everything is restricted to two-phase materials, we can do similar things on polycrystalline materials. These are polycrystals, alpha hexagonal, alpha titanium polycrystals. And here we can actually predict modulus and yield strength. Same ideas, we do PC scores, we represent them by PC scores, and it turns out just about 10 or 12 PC scores here, 10 or 12 PC scores here are enough to produce a very high accuracy structure proof. So in other words, now you can come in with any 3D RVE, with any texture, any grain shape, anything you like, and we'll be able to predict a modulus and a yield strength very fast with high accuracy. It's not restricted to just mechanical. This is flow, fluid flow. So this is permeability. And we are actually showing that the permeability predictions are also pretty good. Keep in mind the ranges as I'm showing you this comparison plots. So usually the challenge is producing something that spans the entire range of predictions. And this is a very large range because you can create a lot of porous structures. And again, here continuity of pore is important. And we are saying that even that is captured well by our techniques. And we are again predicting the expected value and we are predicting the uncertainty, right? So this is the mean expected value and this is uncertainty. Thermal conductivity in woven composites. Out of plane conductivity generally is a harder one to predict because of there is porosity and there is this complex 3D woven structure. And again, we are saying that the methods can do pretty well getting all of that right. Another difficult problem is this is damage and fatigue. So this one is damage. We have done a similar one in fatigue. And here you have microstructure and the interfaces between the soft and the hard material creates damage, they create stress concentrations, and those stress concentrations lead to damage. And there is what is called as a damage parameter distribution or damage indicator parameters distribution. And you can actually predict that distribution. So this is entire distribution. And usually the tail of the distribution is what causes the damage. So when you're worried about damage, you're worried about predicting the tail of this distribution accurately, right? And so again, this entire thing is a tail, but this is the extreme tail, right? So this is only the top 1% of the distribution, right? So this is these are the hot spots in the material. So you can actually predict the occurrence of those hot spots pretty accurately. That everything there so far was mostly structure property. When you get to process structure, it gets a little bit more complicated, but the idea is still the same. So in this case, we are doing microstructure evolution in static recrystallization. The data comes from cellular automata. And essentially what you're doing is, because the microstructure is represented by PC scores, we are building a model for the current PC scores at time t as a function of PC scores at time t-1 to t-h, basically. So given a few time steps of history, can we predict the current values of PC scores? So in general, this kind of modeling is called autoregressive models. And because we're using them with a Gaussian process, we call this GPA, or a Gaussian process autoregressive models. And again, we can make predictions, and we can make predictions of uncertainty. And you can actually see the predictions are pretty good. I mean, in this case, some places you'll see a change, but the line is one of them. One of them is the actual data, and the other is one of them came directly from CM, cellular automata models, and the other data points, the data points are from CA model, I think, and the line is from the reduced model, from the reduced order model. And you can see that it does pretty well. It does almost amazingly well. Same thing can be done at the atomic scale. Here we are predicting formation energies for a very large number of compounds, 1800 compounds here. This work is still going on, but this is what we have done so far. And here we are predicting grain boundary energies and grain boundary mobility. So this particular plot is for grain boundary mobility. Again, in all these parity plots, one of them is what we call as ground truth. In this case, they come from MD simulations. So in this particular case, this ground truth comes from MD simulations. Here, this comes from DFT calculations, density functional theory calculations. And the other axis is always prediction from the surrogate model. So if the models, if they are agreeing, they should all fall on the black line. If everything falls on the black line, it's incredibly accurate, right? But obviously you can't get that, but you get good enough. You can also do fields. So in this case, we are predicting stress and strain fields in polycrystalline microstructures. So this is elastic. So this is now elastic strain, local elastic strain component at each voxel in a polycrystalline. So you can put in any polycrystalline material, any properties of the grains, C11, C12, C33. This is elasticity. I'll show you plasticity soon. And this is the actual local strain field, voxel by voxel, through a midsection of this. Obviously, both of them, both FEM and our method, MKS method, generally we refer to our method as MKS. Our MKS method also produce 3D fields, but we are showing 2D so you can actually compare side by side. And again, the big advantage is that the MKS predictions are very, very fast compared to the real calculation. And they're very broadly applicable. So this is plasticity in a two-phase composite. So this time we are predicting plastic strain rate tensor components, all 6 components of local plastic strain rate. So you can take a two-phase composite and impose any plastic strain, nominally periodic boundary conditions in the finite element simulations. And then we can make a prediction for the local values of each component. Right? So I hope you're getting the general idea. You can also do this on experimental data sets, because so far I've been talking mostly about simulation data sets. So in experimental data sets, you get limited data. So you have to worry about how you're going to handle the limited data. So in this case, we have 27 data points at different temperatures and times and superalloys and the microstructures. Each one data point looks like that, right? And for each one, we take multiple images because the images are not unique, right? So we have a data set. I mean, one would say in experimentally, this is a very large data set because we have 27 histories, temperature histories. And for each one, we have about 20, 30 images, roughly, approximately. So each image is then converted to statistics. So these are statistics. And this is our PC representation. So we have, each one is an image. So each black dot is an image, and we can actually see the patterns. We can see that in general, as you go along the x-axis, the volume fraction of the precipitates goes up. As you go along the y-axis, they become coarser and coarser. So we can actually see patterns that justify that this is a reasonable representation. And then we can, once we do all that and we build models, we can play lots of games. So one of the questions that was asked, that was raised is, what if I give you a different temperature and a time? So this is not one of our data points. If I give you a different temperature and time, it was not one of the data points that went into the training of the model. Okay, so these are test sets that are set aside. And then you say, okay, given this time and temperature, can you predict the structure back? And then we are showing, yes, we can. Left side is what we predict. Sorry, left side is what is the actual experiment. The right side is what we predict. Okay, so left and right are targets. And so you can see that we get most of the features right, and we get most of it right. Okay, so that's all on the surrogate models. So since I'm running out of time, I'm going to speed up a little bit and talk about this experiments. We in the field need high throughput experiments. I would argue that a lot of the current experiments in the material science field are done what I would call as high quality, low quantity experiments, in the sense that we get very few data points when we do them, when we do these experiments. Unfortunately, in this field that I'm talking about, you need a lot of data, because there are so many local scale, local constituents, and you also need multi-resolution data. So it's not enough to know only the bulk performance, but you also need to know the local performance. So we are heavily into indentation as a way of doing it. Indentation, as you can imagine, is fast. We can do it at different length scales. We can go and do it at the local length scales. We can look at each individual phase, or we can do it bulk. The trick is in the analysis. So most people, I mean, this is what you get in raw indentation. Most people analyze the unloading part, which is this one, and they analyze it using Hertz theory. So the Hertz theory is what is here. The argument there is that because you're analyzing the unloading part, my argument is that whatever you get, whatever properties you get here, do not belong to the material that was given to you. They don't belong to the virgin material as given, as received material, but instead they belong to this material that has been disturbed by your indentation. When you do indentation, you're imposing a lot of local plastic deformation. So what you're measuring is actually corresponds to wherever you do the unloading from. So these are the properties of the material at that point. So the only way we think the right way to do indentation analysis is actually to identify the initial elastic portion, which is a tiny elastic portion. Especially in spherical indentation, you get at least this little bit portion. If you do a sharp indenter, then you don't even get this part. But if you do it right, if you apply the protocols right, we explained the protocols in this paper a while back, you can actually convert this load displacement curve that looks like this, where you cannot see elastic plastic transition. You can convert it very nicely into a curve that looks like a stress strain curve. We call this an indentation stress strain curve, and we think it's just like you do different states of stress, like compression, plane strain compression, shear. Indentation is another mode of deformation. So what you get here is an indentation stress strain curve. Analysis is complicated. What it means is complicated, but it nevertheless is that it reflects material response. So then we have, first of all, to convince ourselves that what we are saying is true. We have done a lot of finite element simulations, and we have shown how to scale between uniaxial stress strain curves. USS is uniaxial, like tensile stress strain curves, or compression stress strain curves. They're both uniaxial stress strain curves. And the indentation stress strain curves. ISS is the indentation stress strain curves. We have shown it for different materials using the same scaling factors. So there are only 3 scaling factors you need for isotropic plasticity. And for isotropic plasticity with these scaling factors, you can pretty much convert any indentation stress strain curve to a uniaxial stress strain curve, which is pretty good compared to what you actually get from the direct measurement. So the red lines are direct measurements. The blue dots are what we recover from indentation stress strain curves. In terms of predicting yield strength, our accuracy is pretty high compared to what people are doing with hardness. Using the type of things they're doing, our accuracy is much higher. What have we done with this? We have done a lot of high throughput experimental assays where we change the composition in a material from one end to the other end, and we apply different heat treatments. So we say we have a sample of libraries. So within one sample, we can actually see microstructures, different microstructures because of different chemistries, but also because of different post-heat treatments. Right? This is made by a lens by one of our collaborators. And then we can actually measure properties using indentation. And we can actually see that the yield strength changes dramatically with this, with the post-heat treatment. and we can get very, very, very big differences in yield strength. We also get differences in microstructures, and we're capturing all that data. The idea is that it's high throughput, so you can actually do it fast. You can also do it at different resolutions, so you can actually go into DP steels and measure properties individually of the ferrite. So the blue dots are the measured properties of the ferrite. The red dots are properties of the martensite. So now we're actually measuring locally within martensite regions for different process histories. So this is an annealing treatment. The first letter is annealing treatment. 810 is an annealing treatment. 10 is the cold work after annealing treatment, and 170 is a bake hardening. So the process is complicated, multiple steps, but we can actually track through the process steps and see what is happening to individual constituents. So the red is martensite, the blue is ferrite, and the black is bulk, because we are using a bigger indenter, much bigger indenter. So we're getting a bulk response in the black line. And we can actually make sense. All of this actually makes sense. Unfortunately, I'm running out of time. So the last thing I want to say before I stop is that we can actually apply this to grains, in individual grains, and study the mechanical response of individual grains in polycrystals. Different, these are titanium alloys, these are different polycrystals. So you can actually measure and learn individual properties of individual grades. So how do you get some meaningful physical parameters? Well, you have to do models. So in this case, you do finite element models of indentation using CPFEM or crystal plasticity models. So you can actually build surrogate models. So this is my step one. This is how we build surrogate models, but these models are built based on the finite element models. So at this point, there's no information from experiments. But then we give the experimental data. And once we have experimental data, then we can say, because when we do the models, we are doing it for all kinds of physics. In this case, the physics, for example, is slip resistances. So we are saying the slip resistances, there are 4 families of slip systems: pyramidal, pyramidal C plus A, basal, pyramidal, prism, basal, pyramidal A, and C plus A. And essentially what we're saying is, given those measurements, given the experimental measurements, can we extract the crystal level properties? And we're showing, yes, we can, and we can do it for different chemistries. So there's a lot of information in these graphs, but we can actually get the single crystal elastic constants, and we can also get single crystal slip resistances. And we can get the uncertainties associated with them. Right? Not only we can get the predicted values, estimated values, but the uncertainties associated with them. So we can generate a lot of data here. And what we are currently doing is building the systems where you are in the experiment, you're in the lab. So you're doing all the simulations separately, uncoupled, and you're building this knowledge system. So this is what I'm calling as a knowledge system. And then if you're in the lab, the knowledge system will guide you. It will look at a EBSD map and say, out of all the grains that are there, you're better off indenting this particular grain next. So when you indicate that, then you can do the experiment, you can update the information, and then it can go in cycles. So this is where we're moving towards, we are trying to move towards autonomous experiments. So can we actually get the computer to decide what is the next experiment to do? We're already doing autonomous simulations. So right now, all those surrogate models I showed you are done completely autonomously. So the computer creates the new files, new input files, runs them, gets the answers out, and adds to the data. So, but now we want to be able to do autonomous experiments so that we can then combine the entire thing into what I showed you before. With that, I think I'm going to stop. I think there are a couple of slides about how we are doing this punch test to do stress strain curves again. So we're recovering stress strain curves from punch test. The load displacement curves look like that. The stress strain curves look like that. But I'm going to stop there. I think I'm out of time. So with that, I'll stop here and make a couple of statements and then take questions. I think I'm hoping to show you that, I hope I convinced you that there is a formal way to build materials knowledge systems that can give you decision support in materials innovation. And this is how we think we can speed up materials innovation cycles from the current 15 to 25 years to hopefully something less than 5 years. That's our initial target. And we also believe that high throughput experiments are important. We have to rethink how we are doing experiments and also how we are doing simulations. We need to aim for this autonomous experiments and autonomous simulations, both high throughput, so that you can feed the data you need or generate the data you need to feed these knowledge systems. So with that, I'm going to stop.
Yeah, thank you so much. Thank you so much, Professor Surya. It was really a very wonderful talk about the material knowledge system, which gives the information about the microstructure informatics, data analytics, simulations, all these things. And it is very useful for all these students. So some of our students are also interested to work in this area, PhD students, master students. And this talk will be very beneficial for their career. And I hope that we will continue our interaction in future. And we look forward to see you once you visit to India also. Thank you so much. Thank you so much, Professor Surya. And our director also conveyed regard to you. I informed him that Professor Surya is here today and he will be talking. Actually, he is busy in some meetings, so that's why he could not join. But otherwise, he conveyed his regard. Thank you so much, Professor Surya. Thank you for joining.
Please. Yeah, please convey my regards to him. Thank you.
Sure. Thank you. Thank you.
Thank you. Bye.
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 Yeah. So, dear participants, with this, we end today's program. So, today, yeah. So, if anybody has any question, we can discuss with Professor Surya. He is still here. Any question?
I had a question.
Sure.
Yeah, Professor
I may
Nikhil.
ask.
Thank you so much, Professor Nikhil. You have joined here. Yeah.
Go ahead, Nikhil.
Yeah, good morning, Surya. It's very informative talk. I really enjoyed it.
Oh, thank you.
Yeah, one comment you made in the introduction slides was about the compatibility of different data sets and curation of data sets.
Yes. Yes.
So that caught my attention. Maybe you can give some example, if possible, on incompatibility between data sets and what we can do in order to make them compatible with each other for making these predictions.
Yeah, that's a very good question, Nikhil. I think in many other fields, the way people have solved this in other fields, right? I mean, this data incompatibility is not only to our field in material science or manufacturing in some sense, it's there. In many other fields, what people have done is to put time and effort into these ontologies, right? Essentially schemas and ontologies, right? I mean, so schemas are in my mind, are the lower level versions of ontologies. But essentially, in our case, what we are doing is building a material graph ontology that's going to connect, that captures all all the metadata that is associated with the data. So in other words, if a particular sample produces an SEM image, right? And as the same sample produces another mechanical testing load displacement curve. Right now, a lot of this information is in somebody's, I'm going to turn the video on. I think I turned it off. Sorry. A lot of this information is in somebody's notebook or is in somebody's head. And essentially, that makes it difficult for others to access that. It's not that it's not there, but it makes it incredibly complicated for others to access that. So what we are building now with NIST and other people are these, we are trying to build these ontologies that can describe the relationships between the data sets and also what is inside the data. But these relationships are encoded in the knowledge system, right? Or are they available for people to access? So that's what I had in mind when I'm talking about. But then there are other ones that also it naturally leads to is there are places where there are gaps in data sometimes, and so you can actually do imputation. But again, if you don't have the metadata, it's very hard to do that. You can always do this one at a time, but it's complicated. Did you have something else in mind, Nikhil?
I had a follow-up question actually, because your answer was in the right direction. So microstructure property relationship is the biggest thing in our minds as material scientists most of the time. So have you put the microstructure and mechanical properties, both like images and data sets, both in the same machine learning models and try to conduct predictions out of them?
Yes, I can send you a couple of papers we wrote. Yes, we did, using the same techniques that I'm talking about. Is mostly using spatial correlations and two-point statistics. Spatial two-point statistics. So it's a question of how you convert images to a set of numbers, basically, right? Featureization. That's where the challenge is. So what we have done is basically the same kind of things I showed, and we have a couple of papers in that direction. Obviously, the more information you have, the better it is, right? Because when you say micrographs, is it an optical micrograph? Is there a lot of noise? Is it an SEM, BSE? Different images. There's no one standard image. Different images have different levels of information, and so that one needs to account for that too, in some sense. And those are still unsolved problems, right? We only started. What we did is only very basic stuff so far.
Yeah, I agree. There are a lot of opportunities in this area. Yeah. Thank you very much.
Yeah, there's still, I don't mean to somehow imply that all the problems are solved by any means, right? I don't, I'm just talking about how to establish a formal methodologies, and what we know for now is that simple problems do work, and it does, so it gives us enough confidence that we are in the right direction. We just have to keep pushing forward as a community.
Thank you.
Yeah, thank you so much, Professor Surya. Any other question from the audience?
Hello, hi, this is Dr. Suresh.
Yeah, please go ahead.
Thanks, Dr. Surya. I have worked using the other way, using CalPad, using the phase diagram and estimation.
Yeah.
So I just wanted to know if such methodologies did generate significant data, but in terms of key parameters like transition, temperature, compositions, things like that. Sure. And then that led to determining band gap and things like that. Are such initiatives being done using the material informatics?
Oh, I'm sure they are. I think it's not an area that I'm an expert in, but I'm sure they are. I think there are people at NIST and other places that are doing, right? I think Ikiro is doing some work there.
Okay.
Right, there are lots of people who are in that area. I think the underlying ML algorithms might be may overlap a little bit, because their features are different, right? So
okay.
In my case, I'm more interested in this hierarchy of material structure. So I'm trying to capture the atomic to the mesoscale hierarchy.
Okay, thank you.
But they are able to do this high throughput experiments. I think the Bayesian strategy of design of sequential, that part is probably similar. From what I could hear and I could make out, they're using similar kind of tools and machine learning tools to decide where to do the next experiments and so on.
Thanks. And just a follow up to the earlier question, is there a JSON kind of methodology where you sort of socialize all the data in a meaningful form before you build your knowledge system? Is there something available at this point?
Yeah, I think I think it's still being built. This is what I mentioned as something we're doing with NIST, Zach Trout and James Warren at NIST. We are involved in this. So there is, at this point, there's a website, but there's not much to do. So, but the underlying all that is, there's an ontology, and it does use JSON and other things. So the effort currently is, how do you define the ontology elements in such a way that it can capture all details of process structure property relationships, right? That's so because of the way we approach, we focus everything around process structure property. So it kind of gives us a direction. And so our ontology is all about PSP linkages. So we have defined an ontology. The ontology, there's a paper that describes the ontology. And we built an ontology. We built it, but we haven't exposed it to the broad community yet. But that should happen in a few years, in a year or so, hopefully.
Thanks. And lastly, a simple question, one other question. You showed about the grain size in the last slides. There are some relationships like the Hall pitch relationship, which has survived its almost 100 years. When you see such relationships, or do you take? Do you take it up as it is, or you? How do you handle such things?
So that's what we call as domain knowledge, and what we would call is in the way we look at it, that will be the prior. So almost everything you ask, there's a prior, but you're not sure about it, right? You're not 100% sure about it. So there's an uncertainty. The more uncertain it is, the broader if you think of a distribution, it's a broad prior, right? If it is a uniform distribution, that means you really don't know anything, right? Essentially, right? So that's what it is, right? So we capture that in the priors, and then we then say, okay, given this information, what can we then say about the physics? Yeah. So our strategy is not to ignore the physics. So yeah, there are a lot of people who are saying I can actually completely give away the physics. I don't have to do any physics anymore, but that's not true. In our case, we certainly don't believe that. We actually like to, we think of physics as a data source. Basically simulations or theory as another source of information, experiments as a source of information. And we are asking, how do we maximize all sources of information, right? So mostly from an information theory point of view. We are coming at it from information theory point of view.
Thank you, Professor Surya.
Yeah. Okay. Thank you so much. Any other question? Yeah. So if there is no more question, let us thank once again Professor Surya for your valuable time and joining us. Thank you so much. Thank you so much. Yeah.
Thank you very much. And I really appreciate it. And I enjoyed it. Thank you.
So dear participants, so with this talk, we have ended today's program. So today we had Professor Pedro from Aalto University, Finland, who spoke about the friction-based welding and processing. He discussed the fundamentals and innovations. And then we had Professor Gaurav Mohanty from Tampere University, Finland. He spoke about the in situ mechanical testing at small length scales. And then we had Professor Blake Klein and Dr. Jimmy Campbell from Cambridge University and Plastometrics. And they spoke about the obtaining metal plasticity and failure characteristics via iterative FEM modeling of indentation, the PIP methodology. And then we had the Professor Surya Kalandindi from Georgia Institute of Technology, and he discussed about the AI-based knowledge systems for accelerated materials innovation. So today we had 4 wonderful talks by 4 eminent speakers. So with this, we end today's program, and let me give you the tomorrow's schedule. So tomorrow we will start in the morning, 10 a.m. We have Professor Satish Mukpadnam and Dr. Bhaskar Bocha from Texas A&M University, and they will be talking again about AI-driven characterization and process monitoring for material on demand smart manufacturing. And then we will have Professor Pradeep Menges from University of Nevada, Reno, and he will be talking about tribology in advanced manufacturing. And then we will have Professor David Field from Washington State University. He will be talking about microstructural evolution during deformation of polycrystals with gradient microstructures. And then we will also have the industrial experts. They will be talking about the fatigue and structural testing and about the tribology 4.0. And then we will have Professor Nikhil Gupta from New York University, London School of Engineering. Today also he has joined with us. So he will be talking about reduction in the materials characterization effort, a transform to extract elastic properties from viscoelastic measurements. So I would like all of you to join today morning 10 a.m. We will have wonderful talks tomorrow and look forward to see you. So with this, I thank you once again all. Good evening.